I think we should start, but the crowd is not here yet.
Who's not here yet?
The crowd, yeah, everybody else.
Oh, I see. Okay. Yeah, maybe wait. Yeah, we should probably get started soon.
I can start the opening and then people join up. Okay, let me screen. Right. Hi, everyone. I am Pouya Pezeshkpour from UC Irvine, and thank you for joining us in the first workshop in explainable graph-based machine learning. As the organizer of XGML workshop, we have me, we have Pasquale Minervini from College London, we have Mathias Niepert from Europe Initial Lab, and we have Singh from UC Irvine. Yeah. High-level motivation behind explaining graph-based models is to provide trust for users and shed some light on why these models behave in a certain ways. And to address this motivation as a part of XGML workshop, with the help of our amazing speakers, we are going to cover several topics. We are going to talk about explaining graph models, which is going to cover by Caroline, Freddie, and Xiangyu talks. We are going to talk about adversarial attacks and defenses on graph, which is going to covered by, again, Caroline talk. And we're gonna talk about improving completion and construction of knowledge bases, utilizing the insights from explanations, which is going to cover by Pasquale, Marika, and JP talks. And finally, we are gonna share a state-of-the-art approaches, best practices, and future directions, which is going to covered by Freddie and Rajiv talks. We start our workshop with our first two invited speakers. Pasquale gonna tell us about knowledge graph in Neurosymbolic AI. After that, Caroline will talk about explainable knowledge graph prediction for human AI collaboration. After that, we're gonna have our first two contributor talk, go on a break, come back, and after break, Marika will tell us about explainable graph AI for drug discovery. And Freddie will talk about explaining deep neural networks, the good, the bad, and the ugly. And finally, we will wrap up our workshop with our last contributor talk. During the talks, if you have any question, you can either ask it in the chat section of Zoom, or you can ask it during the talk or after the talk, based on the speaker preferences. Without further ado, I ask Samir to join me here and introduce our first invited speaker. Samir, the stage is yours.
Thanks, Pouya. Yeah, so as our first speaker, we have Pasquale Hitzler. I'm really excited to have him at the workshop. He's one of the top experts in the world in semantic web and AI, and sort of at the integration of those two. So really excited to have him here. Officially, he's the Lloyd T. Smith Creativity in Engineering Chair at Kansas State University right now. Before that, he was at the Wright State University. And even before that, he was at the University of Karlsruhe in Germany. And then before that, he did his postdoc at TU Dresden. I think what I really like about his work is how he's taken stuff in semantic web and AI, which have sort of been separate areas sometimes, and sort of worked at the integration of those two, looking at neural symbolic systems and trying to integrate them way before the recent trend. And in general, his work has been really impactful. He recently got the 10-year award by the Semantic Web Science Association as well. So yeah, really excited to have him be the opening speaker of the workshop. Pasquale, take it away.
Thanks a lot, Samir, and thanks a lot to the organizers for inviting me to give this talk. Let me work on the screen share here. You should see my full screen with the graph now. Now, the other thing I wanted to do is give you all a link to the PDF of the, just a second, chat window here. So I'm putting it in the chat. Well, if it worked, then it would work, but it didn't. Almost. Try this again. Yep. So there's a link in the chat if you want to have an offline version of the presentation slides. So thanks a lot. Let's get started. So I called the talk "Knowledge Graphs in Neurosymbolic AI." And what I want to do is I want to give you a little bit of a, how shall I put it, a potpourri of things we're doing on this topic. I'm still working on my setup. Apologies. Now I have it like I need it. Okay, great. So I'm going to give you a little bit of a potpourri of work we're doing. We're looking at knowledge graphs and neurosymbolic AI primarily from two perspectives, and I'll talk to you about kind of the work we've done on both of them, which is a lot of material to cover. So it will be very overviewish. It will also be rather quick, but there will be plenty of pointers, in particular also to references. And at the very end of the slides, which you now have also offline, you'll find literature references to the stuff, or just get in touch afterwards if you like. So first of all, I just want to briefly talk about neurosymbolic AI. Although for the audience here, it's probably clear what it is. It is really on getting artificial neural networks and knowledge representation as two streams of AI together, and it is actually an old effort, sometimes spelled differently, neural symbolic. And in very recent years, we did a little bit of analysis of number of papers on the topic on key AI conferences. You see the number of papers are really ticking up, and that's not only that; it's also workshops like the one we're currently at. You find keynote talks and so on. So there's really a little bit of an acceleration happening here in recent years, and I'm pretty sure that trend will continue. So what is it all about? Neural refers to artificial neural networks. We talked about that already. Deep learning, of course, is fueling the current AI hype. And symbolic refers to, well, generally computational symbol manipulations of all kinds. You can think algorithms, but more precisely in this particular context, it often refers to symbolic logic, so formal logic as used in knowledge representation. And of course, also in semantic web, which is kind of why I kind of coming from this field, this interests me. Why would you like to bring those two together? You would, for example, like to bring those two together because these both approaches to artificial intelligence are very different in terms of what they can do and what they cannot do, and in terms of applications they enable. Just to pick out a few from the list here, artificial neural networks, connectionist systems. On the positive side, for example, they're very robust to noise in the data, to mistakes in the data, but at the same time, they're very hard to understand or explain, as we know, which is why explainable AI has become such an endeavor. Symbolic systems are just the other way around. They're really brittle with respect to problems in the data, to mistakes, but at the same time, they're relatively easy to analyze and understand. They can work with background knowledge, which for artificial networks is still much more problematic, and so on. But then we have the learning capability on the artificial neural network side.
ISSP during that role, and
all right, we have a somebody not muted. Okay, thanks a lot. We have, of course, on the artificial neural network sides, very strong learning abilities, which are really not at that level for symbolic side. So we have these complementary strengths and weaknesses, and the hope is you get a best of both worlds, which really can kind of, that one side can help the other out. The big question is, how do you do that best? How can you get those two things together? And there's, well, quite a lot of discussions right now on that. And the paper I gave earlier, where we did this analysis of the current trend, talks a little bit about different ways of categorizing this. But I don't want to go into too much detail here, but tell you about the work we're actually doing. Just to mention before I dive into that, I mentioned already, in fact, that it's neurosymbolic is not a new topic. It has been around and for quite some while, and I've done that before anybody really cared much about it, other than in the abstract. So if you're interested in a more Is
he frozen? Okay. Is he frozen for
there's
those
also
as well?
a change, I believe, in terms of what the field does in the last. So there's still some people not muted, so I don't know if the organizer will
Sorry,
look at
Pasquale,
that. If you want to
your
say
audio
something,
was
go ahead.
dropping out.
Oh, right, okay.
Okay, so yeah, sorry.
Yeah, I guess I'll continue if that's okay, or was anything systematically missed?
Maybe go back a little bit. Yeah.
Okay.
As in maybe start the slide again. Yeah.
All right. So what I was saying was neural and symbolic systems, artificial networks, and AI systems based on formal logic have very complementary strengths and weaknesses. So, for example, artificial neural networks are robust to mistakes in the data, which is good. You can do machine learning with them at levels which you cannot do with symbolic systems. But at the same time, artificial networks are also very hard to understand or explain, which is why explainable AI has become so much a topic in the kind of recent advances of deep learning. Symbolic systems are really complementary to that. You can deal with background knowledge, which is much more difficult with artificial neural networks. They're rather intolerant to noise or mistakes in the data. On the other hand, they're relatively easy to analyze and understand. So there's complementary strengths and weaknesses. And neurosymbolic AI is about getting a kind of best of both worlds scenario where you get both of these parts together in a favorable way. Big question here, of course, is how do you do that? One of the things we've done in the paper I mentioned earlier with the overview over the recent rise of conference papers is well, list different categorizations that have been proposed, but I don't want to go into this in detail here, but rather tell you about concrete things we've done. It was mentioned already that there is a bit of a history to the field. The top 3 references here are more historic, so to say. If you're interested, I believe the field has changed significantly recently, as can be seen also from the overview article mentioned earlier. All right, so I said I want to tell you about 2 lines of research we're doing in the lab on neurosymbolic AI, in particular on getting knowledge graphs. And now we're back to the topic of the workshop, knowledge graphs, together with deep learning, essentially. And the first topic is deep deductive reasoners. And the second topic has to do with explainability, which is probably more in the topic of the workshop. But I want to tell you about the first one as well, because I think it's exciting, in particular with our recent results there. So what are deep deductive reasoners? The task seems simple. You take a deductive reasoning system, meaning one that can do logical deductive reasoning with formal logic. And we know there are symbolic systems which can do that very well. And you train a deep learning system to do this. Now, why is this interesting? Well, there's even technical reasons here, like you want to deal with noisy data. Symbolic reasoners don't really do that well. You may want to do it for speed. Symbolic algorithms are often of very high complexity. But perhaps you may also want to look at it out of principle because you want to learn about the capabilities of deep learning for complicated cognitive tasks. In fact, that is a fundamental quest in cognitive science. Artificial neural networks and formal logic are 2 different abstractions of what goes on in human cognition, one from the biological substrate, the other one from introspection. So there's also a fundamental academic quest here in kind of how can we get these abstractions together, in addition to the more technical challenges. So, right, sounds easy. You take a symbolic reasoner, you use it to produce as much training data as you want. You take your pet deep learning system and you just learn it, right? It's not going to be that easy. And that's part of the story I want to tell you about, because it's a really, really tough problem to do with an artificial neural network. Now, but first of all, there's 2 different ways how you can get at that. One of them is you can look at reasoning as classification, meaning you have a set of logical formulas, a theory. Then another formula is either a logical consequence or not a logical consequence. And here you have your classification problem. Another way of looking at it, and this is more important for practice, but also much harder problem, is given a set of logical formulas, you want to produce all logical consequences. Well, under certain constraints, because the set is in general infinite. So you want some finiteness constraints, but that's not a big problem, making reasonable ones. So this would be more a kind of regression system, so to say. You want to get them all in one shot. That scales much better, of course, because you can just produce them all rather than having to query the system each time you want to know something. Okay, so what is out there in terms of work on deep deductive reasoners? Before deep learning, this problem was just completely out of scope. It was impossible to even tackle. Now, in recent years, there has been quite a bit of progress, and I want to tell you about the columns here and what they mean. Each row is essentially a piece of published work on the topic. Logic refers to which logic was used for the reasoning. Now, even if you don't know what they are, let me just say that actually all of them or most of them are out of a semantic web context, both for systematic reasons and simply because it was the people who were working on them. But the main thing is that these logics differ in terms of how complicated they are. Now, how complicated reasoning over logic is, there are formal measures for that which have to do with complexity, but there are also informal measures which are in terms of expressivity of the logic. How powerful does the logic feel when you model? Nobody has ever formalized that. It's tricky, but that is one of the aspects. So you can essentially tune the hardness of the problem you're looking at by looking at an easier or more complicated logic. So that's one important dimension. Then generative, the column generative means, do you have a system which does the generation of all logical consequences, or is it query based? Of course, you want generative. You want a yes in that column. Transfer means, can you train on some knowledge bases, and then the system can still very well reason over new knowledge bases with completely new vocabularies. You know, that's generally a challenge for some deep learning systems, but this is really what we want, because only if we manage that, we don't have to retrain, and training is very expensive, and only then we can actually claim that we have learned how to do logical deductive reasoning. So we want a yes in that column too, and here you see already the problem, right? You have a yes in one of those two columns other than the last two rows, which is our most recent work, right? So achieving that was a problem. Scale, of course, we want high. Nobody managed that. Some is very low, some is low. Low meaning a few dozen axioms, very low meaning a handful, moderate meaning going into the thousands, which is still not enough for practice, of course. And then there's performance, which, you know, in most cases is high, because otherwise you don't get stuff published. Right. So I want to talk about a selection of those, the ones coming out of my lab. Well, not all of them, but some. And in particular, point you towards the last one and how we finally managed to do that, or rather how Monira Ibrahimi managed that, who graduated from my lab this year. A quick view into knowledge graphs, just that you know generally what I'm talking about. Knowledge graphs come out of the semantic web world. Knowledge graph schemas are sometimes called ontologies. Ontologies is the out-of-fashion term. Knowledge graph schema is the in-fashion term. And essentially they are, you can say, data structures or knowledge bases which are designed for easier data sharing, data discovery, data integration, data reuse. That's it in a nutshell. And of course, the underlying data model is that of a graph, or rather of a labeled, typed graph together with a type theory, which is a formal logic. And here we're back to the logic, right? The whole knowledge graph theme came to widespread attention when Google published their knowledge graph, kind of went public with it. When you do a Google search for some well-known name like Laura Keller, governor of Kansas, you get these info boxes, which is a glimpse into a piece of the knowledge graph. Then you can follow the edges, like, for example, the education edge to Indiana University, that would be an education edge. Then you get the box for Indiana University together with search results and so on. So you can navigate the knowledge graph that way. And if you want to put it as a graph, it looks something like this. And you can extract from that also a schema, or usually you have the schema first before you make the knowledge graph, but Google hasn't shared their schema. I'm pretty sure they haven't shared their knowledge graph either, only a certain limited view on the knowledge graph, because I'm very sure internally it's much more complicated than what we see. Otherwise, they can't do what they do with it. So the schema view would talk about classes or types: person class, organization class. Laura Kelly would be in there, Indiana University would be in there, and so on. And one of the key things about the field of semantic web is about finding out how to, well, make these knowledge graphs really work. How do you design them? What are good schemas? What are good tools? What can you make in intelligent tools for integrating and all this kind of stuff? There's W3C standards, rather prominent ones, based on formal logics. So again, we're back to the formal logics. And very recently, knowledge graphs are really taking off quite large scale in industry. This is a paper from 2019, and there's more happening. All right, back to deep deductive reasoners. I'm going to get a little bit of a background now. So let's look at first piece of work, which is not the newest. This was the first one Monire did, where she was looking at Rdfs reasoning, which is essentially reasoning over knowledge graphs. And she used memory networks, which are networks which have been successful in common sense reasoning, common sense linguistic reasoning. Let me tell you what Rdf reasoning is about. So reasoning about the knowledge graph. And I want to do this by an example. So for example, down here, there's 4 statements. Each of these statements corresponds to a node edge node triple, as we call them, in the graph. Like, for example, Barack Obama is of type president. That would be a typing statement. Barack Obama, husband of Michelle Obama. President, subclass of human. Husband of, subproperty of, spouse of, for example. And now what you have in Rdf is you have a small, about a bit more than a dozen, fixed sets of inference rules, such as the one below, which, for example, says if x is of type y, y is of subclass z, then x is of type z. Well, let's translate what that means. Barack Obama type president, that would match this. President subclass of human would match this. Then Barack Obama would be of type human. You have this small fixed set of inference rules, and that's all the reasoning you can do over RDFS. So without much of a type logic, essentially. So this is what we started with, because it's a very simple logic and we knew it's a hard problem. And there has been other work on this, but this didn't transfer. So it's still great work they did, Bassam and Jim as supervisor, but it didn't transfer. And we really wanted to do the transfer to new knowledge bases. So how do you do the transfer? And that took quite some thinking in the beginning. What we ended up with, and I'll talk about this without going through the exact text on the slide. What we ended up with was doing a normalization up front. So we took the knowledge graph essentially, and the question is, how do you embed it? How do you get at an embedding that is into vector space, which is not dependent on things like how you name the predicate? Because how the predicate is named, whether it's called Barack Obama or president or human, is completely irrelevant for the formal logical reasoning. If you do a consistent renaming, if you do a, do we have a sound problem again?
Yeah, I muted them. Yeah.
Okay. If you do a consistent renaming over the logic, over the terms in the logic, then reasoning is still the same, right? You just have to kind of translate it back afterwards. So you have to think about how do you do the embeddings, because they should not depend in this particular case on the terms which you've used in the knowledge graph. So what we did, we normalized the knowledge graph. Essentially, we used everything and encoded it into one-hot vectors. We use specific one-hot vectors for the RDF terms because they're important for understanding the reasoning that goes on. But the rest we just randomly normalized, and we did that for every knowledge graph. And then kind of let the reasoning run. And then if we got a new knowledge graph, we did the same. We just did the random instantiation into one-hot vectors, did the reasoning, and then translated it back and looked how it worked. And that actually worked rather like a charm. So the mechanics here of memory networks, and let me just go to the diagram, is that, well, you have a memory. Which you point to, and you guys are probably familiar with this. The idea is that the system learns how to embed the normalized knowledge graph into into vector space using a triple representation in vector space. And then if you have a query to the system asking, is it true or false, according to, well, the logical consequences in the knowledge which you can apply to the knowledge graph, then what the system does, it looks up the pieces of the memory which are most relevant to answering that question. It has learned those, of course, puts them all together, runs them through another trained network, and then gives you an output, yes, no. Actually, it's not the whole story. We run through this cycle 10 times before you produce a yes, no answer. And that's essentially what happens. And all the pieces are learned, the embeddings are learned, this piece is learned, and so on. So a querying system. Of this table, which is the results, I just want to point you to this right-hand corner. There's much more data here, but that's the piece ones. That's the accuracy of the trained system. You see in particular we're in the 96% with kind of general linked data or knowledge graphs you can find on the web. Knowledge graphs were called linked data before knowledge graphs were a term. You also see lower performance here in the 52% when we threw a particularly hard data set at the system of a type which we hadn't trained before, because it's an artificially constructed one over which reasoning is particularly difficult. But for kind of real life data, we got pretty much the 90s, and that was cool. So we loved that. All right. So the problem now is how to make a generative system. And Moniré got at that, and it took her quite some time and quite some detours. Her first hope was transformers would really work. And kind of on the abstract, there are some indicators that it would, and she just had to give up at some stage. They didn't. And then she moved to pointer networks and gave those a shot, and those actually really worked and very well. Pointer networks have been used for other kind of problems which are very mathematical, like traveling salesman, convex hull, these kind of things. And the point of pointer networks is that they point. So what happens when you run the system after training? You give it an input, which you give as a sequence. And then at some stage, you start reading the output. You read the output by looking what does the network point to, and it points to input pieces. So here, for example, the highest weight would be on this. So that's the first output piece. Then you look at the network again. Next thing it would produce would be this. Next thing it would produce would be this, and that would be a logical consequence. And then you can keep running this thing, of course. So this kind of naturally transfers because you do everything by pointing to the inputs. So transfer is kind of built in this particular case, which is rather nice for our case. So how well did it work? Well, on the right-hand side, you see what happens if you just use a standard LSTM. Doesn't really work very well. Then you see our values, which you got for transformers, different ways of chopping the input. And here to see the results for pointer networks. And this is now without transfer. So kind of the usual 80-20 split, but the training data is pretty similar to the test data. But yeah, with the tokenizer, particular way of chopping the input, we get a 99%. We outperform the Handler-Magni approach, which I mentioned on RDF. Slightly, our approach is much more straightforward. Now, of course, the question is what happens with transfer, which is what we're really eager to see. And it turns out here, we're getting in the 70-80% range, and you're really just using standard transformers. So this is pretty nice, right? And this is a result which is still hot. It's under review at the moment. So we got this summer. But we are very excited. We want to go forward with this because there's tons of stuff to look at. How well does it actually scale? How well does it work for other logics and so on? All right, let's move to a logic which is a little bit more complicated. This is actually also a polynomial logic like RDFS in terms of worst case complexity, but it is more expressive, meaning it feels like you can do more stuff in it if you model with it. First paper we did here, Aaron Eberhard did that as a side project. And I don't want to go in detail through this, just say kind of, you look at the formulas as a particular syntax coming from description logic, don't worry too much about it. Essentially, the reasoning algorithm, if you do a symbolic one, is very similar to RDFS, just in this case, you only have 6 reasoning rules. And if you have formulas which look like the ones on the left, then you produce the ones on the right. Seems to be simpler, right? Still polynomial, feels more complicated, is more complicated, as you will see. So this was the results which Aaron got by using similar approach, several different approaches of LSTMs, just vanilla LSTMs. And you see what we manage is we get in the 15% range, which is of course not great, right? But we beat a random reasoner, which is much worse. But this was nothing to be proud of. So, but it was the first result we got. It shows how difficult the problem is. And then of course, bring in again pointer networks. By the way, I should mention, Memory tried her memory networks on EL and it completely did not work. She didn't get anywhere. So the memory network approach did not carry over for EL. We would love to know why. We have no clue. But with the pointer networks, it actually worked really well. This is already with transfer. And you see that our results are, well, depending on the size of the knowledge graph, in the 60–70%. If it's larger, then we kind of go down here. So we have to look into that, how we can push that. But you see this works really well. LSTMs really suck. And transformers are nowhere near. So this is where we are. And we're very happy about that. We have no idea how it does for more complicated logics. We have to look at scale, etc. But this is essentially what we have. All right. So this was the first thing. I'm really excited about that. But I'm also really excited about the second topic I want to talk to you about very briefly. And the second topic has to do with explaining deep learning via symbolic background knowledge. Again, knowledge graphs come in here. Why? Because, well, that's our background knowledge. We're semantic webbers after all. So why are we explaining via background knowledge? Well, I probably don't have to explain why we want to explain. We want to understand the behavior of a neural network above kind of what you usually get, which is just a statistical assessment. We want to understand, why do you produce this output? We probably even want to, at some stage, go towards understanding what goes on inside the network. Can we explain internal states of the network? Now, the point is that a lot of explanation work actually explains in terms of input features, like, for example, highlighting part of the input image. And that's, of course, nice in certain cases. But really, if you think of what a human wants, you want an explanation in much more abstract terms. If you ask, why did you put your queen here, chess program, Lila, then you don't want the highlight of part of the board. You want a high-level explanation, like centralizing the queen, for example, right? Which is a high-level concept chess players are familiar with. So you want to explain in terms of background knowledge. Yeah, so how do you do that? How do you connect that? And this is a schematic overview, how we get at that. And we have preliminary results. We don't have really final ones, because it's actually turns out that there's difficulties on very different steps of achieving this. Schematic overview. Say you take training images, and with the training images, you also have annotations for these images. Could be objects on the images, could be other things having to do with colors and whatever, or even metadata to the images of whatever type you may want to have. You have some classifier, for example, which makes scene classification, just to give an example. And then what we do is we map the input images into background knowledge. For example, by taking annotations of the images like objects and mapping them into background knowledge, which is a big knowledge graph. In our case, it's a big class hierarchy, so a knowledge graph schema if you want. And then we want to see, what does the system do? Kind of, for example, understand errors the system makes, look at all the images it makes errors on, and want to see, can we find commonalities regarding the background knowledge on the error images. And the mechanism we use for that is concept induction. I need to explain to you what concept induction is in order to understand what's going on. Concept induction is about the following. You take symbolic, so this is a symbolic system. You take symbolic representations in formal logic of things, like, for example, here in this very old example, trains, right? And the types of cars and shapes and number of wheels and roof or not of these trains. You pick a logic and represent it. And then you take a set which you call positive examples, a set which you call negative examples. And concept induction is about making a logical formula in one free variable, so a set expression, essentially, which tells you what distinguishes the positive from the negative examples. And for example, in this particular case, the L learner, which is probably the most mature mature system, DL stands for description logic, by the way, not deep learning, gives us an output which, if you translate it into set notation, means on the positive ones are trains which have cars that are both closed and short, right? And that's an answer here. So this is what concept induction does. And we wanted to apply that to our, explaining AI systems behavior. The first problem we ran into was scalability, because if we want to do this, say, for hidden, states of collections of hidden layer neurons, we're going to have to go large scale. We also have to use very large background knowledge. we'll also have to use very large background knowledge. And it just turned out that with DL Learner, we couldn't do that. I'll skip that because I have a graphic for this. DL Learner didn't scale to the task. So the first thing, and there was a major piece of work, became a AAAI paper, was finding a way to scale. We made a heuristic algorithm. The system we call is easy. It's still very beta. It's not as easy to use as DL Learner, far away from it. But, well, yes, it scales much better. The runtime on the left, note this is a logarithmic scale. White is our system. And this is actually cutoff here. While on the right-hand side, you see performance comparison between the two. And the horizontal axis is different benchmarks scaled by amount of data used. For the last two, DL Learner didn't even produce a result. It just gave us the default answer, which was still kind of almost 40% inaccuracy. And for the last one, we actually could not compute the exact accuracy of our system because it was prohibitive, because you need to run complex reasoning algorithms over them. Anyway, we were rather excited about kind of, in particular, when DL Learner gave up, we were still able to do rather well. All right, here's an example what we did. ADE20K data set. Objects annotated on the images, like for example here, sky, road, sidewalk, building, truck, and so on. We give it positive images, negative images, give us an explanation for the positive versus the negative. This was our first feasibility study. We used Sumo as background knowledge, which you may know, 25,000 classes, a class hierarchy easy. Regretfully, at the moment, can only ingest class hierarchies and not more complicated background data. And answers we got, for example, was contains a transitway or contains a land area, which are terms from the background knowledge and not from the annotations. So this is important here. Give you another example, which may even be more interesting. Here we gave us positive examples, mountain images, and as negative examples, just some random stuff. And the system came back, one of the answers it gave us was, contains a body of water. It's not what you expect from mountain images. We went back to the images, looked at them, turns out, every single mountain images contains a body of water, right? Talk about bias in your data set, talk about finding problems which you wouldn't have noticed otherwise in order to kind of improve the diversity of your data set for better training, for example. So this is kind of what we wanted to get at. Next step was substituting Sumo with something more expressive. That was also a bit of work. In the end, we settled for a curated Wikipedia class hierarchy because it's just much richer. It's of course also not a very nice class hierarchy, but then, well, we're doing machine learning, right? So we can live with some noise. What we ended up with in the end was a non-cyclic. We had to break cycles. Don't want to talk in detail about how we did that. We needed to break cycles, which are in this crowdsourced Wikipedia class hierarchy. Ended up with a hierarchy with kind of 6 million individuals and about 2 million concepts. So this is something we could really work with then. We did we ran similar analysis, and let me move on because in the interest of time. And did a comparison of Wikipedia results versus Sumo results, which just turned out that we are actually able to fit our data much better. So we're getting higher accuracy in our results. That was rather nice. It was also rather recent. And so the rest I just need to mention because this is stuff that we are still working on, but we have not published and we cannot publish yet. But what we're doing on a high level, and this is the piece I can share, is we're working on how good are these explanations for a human observer. This is one thing we're working at. So we may have results in a few weeks even perhaps, and then able to share them. We're working on two other things. Now that we had all these pieces in place, which took quite some time and work and years to get in place in the right way, because you always run into a lot of dead ends before you know how to do it. We're looking at two other streams in particular. One is, can we use an analysis of outputs of deep learning systems, in particular the errors it makes, to find commonalities in the errors, and then change our input training sets, retrain, and hopefully get better outputs. That's one of the things we do. So essentially the idea is you run, for example, false positives against true negatives, get explanations for the false positives, and just make sure you have more training samples of these types, and the types are given to you using concept induction. So that's one stream we're trying. Another approach we're doing is we're starting to look into, can we analyze hidden layer activations? And that is, of course, really much more tricky, because here the information is distributed. So presumably, nobody really knows, right? But that's why we're doing this. Presumably, if there is tangible information in hidden layers, then it is encoded in a distributed way, meaning it's sets of neurons firing together. And then you have to ask, which sets are you looking at to analyze? Once you have a candidate, you can look whether you get a meaningful explanation using concept induction. But if you say have a hidden layer with 2,000 neurons, then you have 2 to the power of 2,000 possible options of picking a subset. That's completely prohibitive. So we need to look into some smart ways of doing that. And the problem, of course, the other problem, which we always have with this type of analysis still at the moment, is even if we get some candidates and run our analysis, we may not actually be using the right background knowledge, because what we think the network may conceptualize with may not actually be what the network conceptualized with. So for example, some of the preliminary studies I mentioned were run on objects on the images. Is this really what the network, does the network actually detect objects before it produces an output? Probably not. It probably does other stuff. What is the other stuff it's doing? Things like edge detection, right? Or kind of general arrangements or pattern arrangements or rectangular stuff, things like that. Probably more likely, but nobody really knows. So there's a lot of variables to look at and a lot of experiments to run to see what in the end works out. All right, so in terms of conclusions, right? Bridging the neurosymbolic gap is still a major quest. And I think it will remain a major quest. I also think it is one of the really exciting ways of going forward, medium and long term. Because the deep learning hype, just the pure deep learning hype will actually, boil down at some stage. And there is already something happening, as mentioned earlier, that people are trying to improve pure deep learning by getting more symbolic into the picture, more background knowledge, things like that. Research on deep deductive reasoning, in my opinion, is at the heart of neurosymbolic artificial intelligence. Why? Because deductive reasoning, symbolic deductive reasoning, is central to knowledge-based systems using formal logics in knowledge representation reasoning. So we're addressing the central task in that subfield. But try to do it with deep learning. Explanation of knowledge graph of AI systems, in particular deep learning, using knowledge graphs. Well, I think if you really want to get something tangible out of explainability, you need to work with background knowledge. Whether it has to be knowledge graphs, I don't know, right? It's just what we try and see where it works. Whether it has to use concept induction, probably not necessarily, right? But it's a nice tool if you want to deal with logics. So this is what we're trying. Other things should be tried as well. But I really think you need background knowledge in order to make explainability really work, and not just making the expression of something that works, or something that works in only specific cases. So that's the kind of general thrust, I think, needs to be taken there. And I'll stop here. Just in time to leave a few minutes for questions, and please feel free to ask those. And I see already some questions in the chat, so let me look at that.
Yes, I can sort of start off with one, I guess.
Yep.
So this is from Pouya, which was more about how does the mapping take place to the background knowledge? And I think I have some related questions about that, but yeah, maybe we'll start there.
So what we currently do is, but this is just what we currently do. What we currently do is we use data sets that already have annotations. So for example, ADE20K has annotations of objects. Or you find a Google Open Images, I believe, has also annotations which are crowdsourced. So we use these annotations, and then what we use is we use for example, just some string matching in this case, which matches with names of Wikipedia pages, because we're using the Wikipedia category hierarchy as background knowledge. So we match with Wikipedia page names. And then on the Wikipedia pages, we have the categories listed. And that tells us which categories we should map to. So this is what we're currently doing. Once you're and this works, of course, with the Wikipedia concept hierarchy. Otherwise, it's a pain, right? So you have to find a way how to do that. And yeah, it's not straightforward. If you don't have annotations, well, you either have to create annotations, whatever, use Mechanical Turk or something like that. Or, you know, even more exciting, use some deep learning system that can, for example, get objects, right? Recognize objects. But for our case, this would add another failure point, possible failure point in the system, right? More uncertainty. So right now we're trying to use hand annotated data. So that's what we do. I
see. Yeah, that's good. Just related to that, I guess. So when you do these explanations, I'm trying to understand where is the line between explaining the data versus explaining the model, right? So like the body of water thing is a property of the data, and it's possible that the model sort of latched onto it, or possibly it's just a correlation between the label and that feature, but maybe the model actually knows the mountains and is looking at the mountains. So like how do we differentiate that, and how do we go about thinking about that?
Yeah, excellent point. Excellent point. So the way I think about it is kind of getting at the model. Well, on the one hand, getting at what the model does by looking at its behavior. So this is kind of how we think about it. And this is, of course, only one aspect, and certainly does not explain, you know, if you look at just the output behavior, it does not explain what's going on inside the model. But if you find an explanation for, or, you know, a commonality using concept induction among all the things which produce true positives, for example, false positives, then at least you understand that the system makes a systematic error, which you may not have been able to observe using the you know, without the background knowledge analysis. Which then allows you to act in certain ways, to, for example, say, well, okay, for certain types of images, we're just not going to trust the model as much because we know it makes a lot of mistakes, right? For example, or you can start retraining, things like this. Things get much more interesting, I believe, once we manage, and that's still completely open sky, to actually patch explanations to activation behavior of sets of hidden neurons. If we manage to do that, in a convincing way, then we're getting much closer to internal representation. So what does the system detect internally, right? What are the things it latches onto which then produce the output? And I think then we're getting much closer to understanding what does the model think, if you want to put it that way, but we're still not there, right? This is something we're working on, but we don't have any results to show at this stage. But yeah,
I think it would be nice to sort of think about what you've been able to do is sort of give a hypothesis that body of water makes the model predicted. And it would be good to sort of be able to somehow test that. It's very difficult to think of in images, but like, hey, I'm going to remove the body of water and see if it still predicts mountains.
Right, and you can do that. Right. So, for example, if we see body of water, right, and that as for example makes whatever wrong classifications, for example, right, then what you can do is if you get that out of the analysis, and of course you can take new images which have or have not a body of water and see whether you get the same error behavior. Right. You can do the same if you attach an explanation to some internal activation pattern. Right. If you say, all right, this internal activation pattern, you know, is in our analysis seems it's very often activated whenever we have wide rectangular shapes, right? Just to make something up. Then of course you can test that by getting other images with wide rectangular shapes and images without wide rectangular shapes, and just checking whether it really, the activation pattern lights up in the same in the situations in which you actually have one of those, right? So again, that's kind of more testing, but you're getting an insight into what's happening inside of the system if you can do this verification.
Yeah. Okay. Yeah. Latisha, do you want to ask your question?
Hi, am I audible?
Yeah.
Oh, perfect. Okay. Thank you. Thank you for the amazing talk. I really found the idea of using schemas and then concept induction quite intuitive. I was wondering if, do you already know, or do you have any ideas for other techniques for, using knowledge graphs for explanations? For instance, could embeddings help in this task in some way, because they already are in the high dimensional space with vectors?
It's not clear to me, right? So just off the top of my head, it's not clear to me, how. So what you need to do is kind of, you need to think of an architecture. What would you be able to do with those embeddings? It just seems to me that if you have a system that kind of works on images, right, and makes internal representation of images, and then you have ways of trained ways of creating knowledge graph embeddings, then I think just the way these things are represented in vector space, even though it's the same vector space, right? It's not clear how to compare them or do something with them. So I don't think that's at all obvious, right? I believe the general discussion, I'm not really familiar what has been going on in that area very recently. But I think the general discussion is about using knowledge graphs as background knowledge, right? So that's the kind of general idea. But I'm actually not familiar what other things have been done there in the recent whatever year or two.
I see. Okay, thank you so much.
Of course.
Right.
I think we're out of time as well. So thanks a lot, everybody. And if there's more questions, please feel free to reach out by email anytime. Thanks a lot.
Thank you, Pasquale.
Okay. Thanks, Emir, and thank Pasquale for the amazing talk. I just want to mention out again that you guys can ask your question in the chat section of the Zoom. Without further ado, I'm asking Mathias to join me here and introduce our next invited speaker. Mathias?
Yes, thank you very much. I'm very happy to be here. It's been a very interesting 30 minutes, an hour. It is my pleasure to introduce to you Caroline Lawrence. Caroline obtained her doctorate degree from the University of Heidelberg in 2018, where she worked in the Statistical Natural Language Processing group. During her PhD, she worked on machine translation and question answering problems. After her PhD, she joined NEC Labs Europe as a research scientist. In the few years at NEC, she has published several first author papers at top conferences and has not only excelled in research, but also at using research outcomes for meaningful applications. Her joining the machine learning group at NEC was one of the best things that could happen to me professionally. She also has won a Best Paper Award at AKBC. I hope you all have heard about this particular line of work, and has been a popular invited speaker at numerous events. Most importantly, though, she's an awesome and kind colleague, and I'm very happy to have her in my team. Caroline, I'm looking forward to your talk. Please take it from here.
Thanks a lot, Matthias. Hello, everyone. I'm really happy to be here. Let me just share my screen. Okay, I hope you see the slides now. So the talk today is about how we can go from knowledge graph prediction to making these predictions explainable, and then in a second step, how we can move towards human AI collaboration. And with this, the talk is also split in exactly those three parts. So first, a very brief recap of knowledge graph embeddings and how we can use them to infer new knowledge. And then second, we look at how we can make those predictions explainable with the method called gradient rollback. And then third, how can we move towards human AI collaboration? And for this, we developed an interface called Explore and Explain, where we can interactively explore the explanations. And with an application in mind, we have here an example from predicting polypharmacy side effects. So let's have first a brief look at what this looks like. So polypharmacy means that we're using more than one medical drug at the same time. And as you can imagine, this can often cause side effects. So it would be important to know what would happen. However, this is a difficult subject to research because there are so many possible combinations. And often when researchers do this, it's more of a trial and error procedure. And also testing a particular combination is very time and resource consuming. So in this task, the question is, how can AI help? And drugs target proteins to cure disease. So we can use this knowledge to set up a knowledge graph with known relations between drugs and proteins. And then based on this knowledge, we can use AI to predict unlikely side effects. So here's an example. In this knowledge graph, we have drugs as well as proteins and some relations between them. But we don't know the relation what happens when someone takes the drugs polyperidone and calcium at the same time. So AI can help in the following ways, and those are the 3 steps outlined. So in the first step, we build a biomedical knowledge graph, and then we can use knowledge-based completion to predict novel interactions. But then in the second step, of course, a human wants to know why a certain prediction was made. So we want to use explainable AI to explain those predictions. And then in the third step, or moving towards a more human-centric AI, we want to also visualize the predictions as well as the explanations so that we can move towards human-AI collaboration. And as we move through these different tasks and we want to have explanations helpful for humans, so the question is how to best evaluate these settings of how good an explanation is. And here we are following a taxonomy from Doshi Willis and Kim from 2017. And here they listed 3 steps, where from the left, we're starting with an easy evaluation, and then we're slowly moving towards a more difficult one. So the first step would be intrinsic evaluation. So it makes sense to first check that the explanations produced do make sense intrinsically before involving human users, because it's often more time consuming and expensive. But once this is established, you want to start out with some simple tasks where you show explanations to human users. And once you verify that this works as well, then it's time to look at real tasks. And then finally, once we have this established in real tasks, then we can move towards human and AI collaboration. And this is exactly the 3 steps we want to go through in this talk. So Brady and Rollback will have the intrinsic evaluation. And then explore and explain is our next step, where we move towards simple tasks. And then we will finish with a brief outlook of what we want to move towards too, so we can have real tasks with human users for human AI collaboration. And with this, let's head into the first part, where we just briefly recap knowledge graph embeddings. So just to make sure we're all on the same side, we're in the setting where we're given a knowledge graph, and the knowledge graph consists of triples T, where each triple has a subject, a relation, and an object. And we will later train a knowledge graph embedding model, and we assume that we're given a training set, which is the set of known triples. And then based on this, we want to predict new relations. So if we have polyperidone and calcium, we cannot use knowledge-based completion to figure out what likely side effects those 2 drugs will have. And a knowledge-based completion model will, for example, tell us that taking polyperidone and calcium together will likely cause pain. At NLE, we developed a system for this, and it's called KBLearn, and it's a combination of experts. And here are 2 of the experts. The first one is a rule-based expert. So here we have simple rules such as A located in B and B capital of C. And this results in meaning that A is also located in C. Of course, those rules can get more complex, but ultimately they're still human understandable. However, they often perform worse than our knowledge graph embedding model. But our knowledge graph embedding model, on the other hand, is a black box. So while it might have the better performance, it's not explainable. So we originally set out with the research question, how can we make such knowledge graph embedding models explainable? And before we look at how we can make them explainable, here's one more definition that was important to us. and that's the definition of faithful explanations. This means that the explanation that we return actually represents the true reasoning process of the model. And here's a counterexample to give you an intuition what it means when the explanation is not faithful. Let's assume someone asks, why is the sky blue? And then a possible explanation could be because someone painted it blue. But while this is an explanation, this explanation is not true, so therefore it is not faithful. In contrast, we want to make sure that the method that we develop does deliver faithful explanations. And with this, we head into the second part, which explains gradient rollback and how it can make the predictions explainable. So our goal with gradient rollback was to make sure we have faithful explanations. And gradient rollback works by explaining a prediction where we return the training instances that had the largest impact on making a prediction likely. And as I mentioned, we're using knowledge graph embedding models, and we apply them to knowledge-based completion as well as recommender systems. And what is great about gradient rollback is that we can derive a theoretical bound on its approximation error. And we've also support this with evaluations that measure how faithful the explanations are returned from gradient rollback. So this is the part of gradient rollback. First, we'll briefly look at what knowledge graph embeddings are. Then we look at the method of gradient rollback itself, followed by a very brief outline for the proof, and then the empirical results. So here just a brief recap of what knowledge graph embeddings are. In the knowledge graph embedding, we have vectors that represent each entity in relation in the knowledge graph as a vector representation. And we also have some scoring function f, and with this we can judge how likely a triple is. And different scoring functions are possible, and the one that we focused on first was dismod, because it's both easy and popular and competitive. And dismod simply calculates the inner product of a triple. We then learn what good vector representations are via gradient descent, where we increase the likelihood of the known triples while decreasing the likelihood of random negative examples. And it's exactly this procedure that we want to make explainable. And intuitively, gradient rollback works like this. During the training process, we measure the influence gamma. So gradient rollback tracks the parameter changes of each triple as we make an update to the knowledge graph embeddings. And as an example, we can then later explain a prediction such as volunteer park located in USA. And the explanation is in the form of the training triples that cause this prediction to be likely. And here the explanation is that because Volunteer Park has a sculpture of William H. Seward, and William H. Seward is born in the USA, because of this, the model concluded that Volunteer Park is located in USA. But let's now look further in how exactly gradient rollback works. Gradient rollback has two steps, and in the first step, we track gradients. This is done during training. This means that we record the influence that each training instance has on a model's parameters. Let's look at what this means in detail. So this means that we want to track the influence of the trained triple D prime. And we want to measure its contribution of this trained triple D prime on the model's parameters at the time step t+1. We do this by looking up the previous influence of the trained triple D prime, and then also taking the gradient from applying the loss for the current training triple. This means that at the end of training, we know for each trained triple D prime, the influence that accumulated over the entire training process. And with this information, we can go to step 2, where we roll back the influence. And with this, we can explain a prediction by identifying which training instances had the largest impact on making the prediction likely. Let's look here at the step-by-step how this works. So we want to explain some prediction D. And for this, we have to go through the following steps. For each training instance D prime, we do the following. First, we remove its influence. So we compute a new set of weights here called WGR. And we do this by taking the final model weights. And from this, we subtract the influence of D prime that this had on parameters of D. So this means that an explanation D prime can only have an influence on D if they have at least one triple part in common. Once we have the new weights, we do the following. We look up the probability that the triple D has under the new weights and compare this to the probability that D had under the final weights. And if we saw that there is a probability drop, then we can conclude that this is a possible explanation, because this means that having this training triple D in the final model meant that the prediction for the probability for the prediction became more likely with this training triple present. So once we've done this for each training instance, this means we can split the training set into two parts, into the triples that caused the probability to become more likely if it was in the training set or it didn't. So ultimately, we can return a ranked list of training instances as the explanations. And in this ranked list, the top one explanation means that it's the training instance that would cause the largest probability drop if it were removed. Next, let's look at the outline, because crucially, how well gradient rollback works depends on its approximation error. Or in other words, how well can gradient rollback approximate the true influence of training samples? And we can look at this by comparing two numbers. And the first one is the approximation of gradient rollback. This is the weight derivation WGR that we just saw on the previous slide. And we compare this to the value that we get for the true behavior after retraining. And if we subtract those two values and an expectation that they are low, this means that we have a low approximation error. And in the conclusion of the proof, we can say that gradient rollback can approximate for any training triple D prime in the training set the changes of a scoring or loss function one would observe if a model were to be trained on the training set without that training instance D prime. And ultimately, we can show that the approximation error is an expectation lower than known bounds on the stability of gradient descent. So with this, we can conclude that the approximation error of gradient rollback is indeed small enough. And with this, let's look at some empirical results. And to recap, this is the stage we're at in the evaluation steps. So first, we want to make sure that gradient rollback is intrinsically good before we move on to showing this to human users. So here's how we measure the intrinsic evaluation. Remember that our goal is to make sure that we have faithful explanations. So those are explanations that represent the true reasoning process of the model. And we evaluate how faithful the explanations are with the following method. For each prediction, we do the following. We take from gradient rollback the explanations it's returned for a prediction, and we remove those from the training set. And then we retrain the model without those explanations in the training set. Once the model is trained, we can check how the prediction changes, if the probability dropped or increased. This allows us to define two evaluation metrics. And the first one is PD percentage. This is a percentage of times the prediction probability drops when the explanations are removed from the training set and retrained. The other evaluation metric is TC percentage, which is the percentage of times the top one prediction changes. And this is important for us here because the predictions that we're trying to explain are the top one predictions of the model. We have 3 datasets. 2 are knowledge-based completion datasets and 1 recommended dataset. And here is a brief outcut of the results that we got. So we have on one hand gradient rollback, and then we have the baseline NH, which randomly deletes triples in the neighborhood of the prediction triple. We also vary the number of explanations that we delete. So we have either just the top explanation, the 10 top explanations, or all explanations as identified by gradient rollback. And we can see here for the PD percentage and for 2 of the data sets that gradient rollback always outperforms NH. And this also carries over to the other data set and the other evaluation metric. So with this, we can summarize gradient rollback in the following way. Gradient rollback has a two-step procedure, and in the first step we track the gradients, where we measure for each training instance the influence it has on the model's parameters. And in the second step, we roll back the influence, which allows us to explain a prediction by identifying which training instance had the largest impact on making the prediction likely. And our goal was also to make sure that the explanations of gradient rollback are faithful. And for knowledge graph embeddings, we could show with a theoretical bound on the approximation error that this error is indeed low. And we could also verify empirically that the explanations returned by gradient rollback are faithful. So with this, we evaluated gradient rollback intrinsically. But we want to make sure that ultimately the explanations help humans in some way. And here we've mainly focused if they can help humans in their decision making. And with this, we head into the third part of the talk, where we want to explore the explanations interactively. And with this, go a step closer towards human AI collaboration. And this part is split into two parts. First, I'll explain what the interface looks like that we built. And second, there'll be some initial experiments, as this is still a work in progress. So now that we have the explanations from gradient rollback, we want to find out, can the explanations improve human decision making? And in part, also one of the issues that we still have is that gradient rollback might return a very long list of explanations. So a secondary goal is to find out which of the explanations that gradient rollback returned are actually most helpful for human decision making. And to address these questions, we developed a user interface with 3 modes. We first have an expert user mode, then there is a lay user mode, and finally the mode for experiment participants with which we want to try to find out the answers to our research questions. You can already see a small screenshot on the right here, but we will go through the different parts of the screenshot next. So first is the expert user mode. So the expert user has the ability to upload the predictions alongside their explanations in a JSON format. And once the upload is complete, the user can choose a prediction from the list. And once they click on a list, the next interface is loaded, which shows the explanations for this prediction. So in that interface, we have the prediction that we want to explain, which here is Sophia is niece of Victoria. We then also have several filters. So for example, at the bottom, we can say we want to load the top K instances. And here we chose the top 10. And then in between, we also have a couple of different filters for what constraints we want our explanations to fulfill. And there is different constraint settings for each part of the triple of an explanation, so either pertaining the head, the relation, or the tail. And in this particular example, we say that the tail must be equal to what the prediction of the head is. So here we can also use the shorthand and capitalized head to make sure that the head that we want to load here is whatever the head of the current prediction is. And then once we are satisfied with the filter that we want to apply, we can click the apply button, and then next the explanations will be loaded. We can then also again change the filters and hit the apply button again to load additional explanations on top. So the advantage of this interface is that it's easy for the expert user to visually explore the different explanations returned by gradient rollback. And once the expert is happy with a certain filter setting, we can save this filter setting and then make sure that when we send a link to lay users to look at the explanations, the same filters are applied. So of course, the expert user also sees this, but the lay user actually does not see the filters. The lay user only sees the table of the explanations as well as the graphical interface, which I'll show next. So in the table, we have now only the explanations as they were filtered by the expert user. And in the last column, we also have a column that is marked as helpful, and we have this so that people can tell us which of the explanations was actually helpful to them in their decision making. And next, we also have the graphical view. So here we have the explanations that we just saw in the table format, but represented graphically. And here people can also drag and drop the different nodes and explore the explanations in this way. The prediction is also shown and it's red here, and all the explanations are in blue. And people can also click on the links to mark a certain explanation as helpful in the graph format. For the participant, they are first redirected to this landing page. And here we have the instructions shown as text as well as in a video. And once the participant is ready, they can click the start button. And from this moment on, the time measurement will start. And here then the predictions will be shown one at a time to the user, and they can explore the explanations. And their goal is to find out whether they think the prediction is correct or not. And ultimately, we ask them to fill out a feedback form. And once they filled this out and click the submit button, they are shown to the next prediction. So let's now look at the initial experiments. So to recap where we are in our evaluation pipeline, we are now in the second step where we want to check how well the explanations work for simple tasks, but with real human users. And for this, we have 3 research questions. And the first one we already just touched upon a little. So here we want to find out, based on the explanations, can users decide if a prediction is true or not? And for this, in the feedback form, we ask them, do you think the prediction is correct? And here we have a yes and a no button, but we also decided to add the I don't know button because we found out that sometimes the explanations neither contradict nor confirm the prediction. Then the second research question, we ask, what kind of explanations are considered helpful by users? And if we can find out what are helpful explanations and which are not helpful, can we then help users to save time by presenting only the selected helpful explanations? And we can then use the information from the table that we saw previously, where people can mark different explanations as helpful. And finally, we would also like to figure out if users prefer the table or the graph view. And because we wanted to start with a simple task where we understand the dataset well, we started with the kinship dataset because it has 12 commonly understood relations from family trees, such as is nephew of or is mother of. And with this, our hope is that everyone can determine if a prediction is true or false if all the relevant information is given. What is also very helpful is that based on just one triple, it's not possible to determine whether it's true or not. And with this, we can remove any bias that someone might have because of prior knowledge. And here's an example. So if we have the prediction, Mary is mother of Tom, if this is all the information that we are given, then we cannot tell if this is true or not. But once we have the relevant explanations given, we can tell whether it's true or not. So if we learn that Mary is mother of Mark and Tom is brother of Mark, then a human user will be able to derive that yes, this makes sense and the prediction is indeed correct. And this was our first experimental setup. We created a balanced data set of 15 true and 15 false predictions. In the first experiment, we show all gradient rollback explanations that we have for each prediction. And those were on average about 23 per prediction. And in the second experiment, we then used from the first experiment, all explanations that were marked as helpful. And then we only showed these to the user. And with this, we wanted to explore if we can help people to save time by showing them only the selected set of explanations. And if you look at the table, this allowed us to reduce the 23 explanations down to 2. So this is also, of course, a lot less information that people need to look at. And what we also report in the table is the accuracy. So how often did the users correctly decide that a prediction was true or false? And we also measured the time it took for each prediction before a user was confident enough to fill out the form and hit the submit button. And in the first setting where we showed all explanations, we can see that the accuracy is very high. And as this is a toy data set, this makes sense. And this is something that we will also assume will drop later on when, for example, the task is a lot more challenging and the relations are more complicated. But at least in this initial setup, we can say that, okay, yes, users can reliably determine if a prediction is true or false based on the provided explanations. Then in the second row, in the helpful column, this is the second experiment where people saw only the explanations marked as helpful. And here we can see that the agreement between different human users matches because the explanations that were marked as helpful by the first set of users was indeed enough for also the second set of users to obtain the same kind of accuracy. But at the same time, we can also see that because people now have less explanations they need to look at, we can reduce the time a lot. So people save over 1.5 minutes by now only looking at the relevant explanations. And in this context, we're also curious for later human AI collaborations to support the human. Can we automatically predict which explanations will be helpful? Because if we can do so, then this will reduce the load on the humans by a lot. And then finally, our last question was whether users prefer the graph or the table format. And here we mainly ask for feedback. So in our current experiment, we had in the form an option for people to let us know whether they preferred the graph or the table. And here we found that all users preferred the graph format. So with this, we're currently at the stage where we confirmed that the explanations and the setup works for simple tasks with real human users. But now we want to move on. We want to move towards real tasks, and with this towards human AI collaboration. And we want to do this in 2 ways. We first also want to scale up the experiment, find a bigger data set, a more realistic data set, and also, of course, with more people. And here I'd also be happy to hear if anyone has any suggestions for a data set, as well as if there's any other research questions that would be interesting to include in future experiments. And on the other side, we also want to extend the interface itself. So we want to, for example, strengthen the interactive component. Currently, people see only the explanations as they were filtered beforehand by the expert users. But we could also add other features where we allow people to explore more parts of the knowledge graph, maybe not even necessarily part of the explanation set, just so people can follow up to verify whether a prediction is true or not in a way that they find important and not necessarily just what the AI system considers the explanation. And especially this component we think would be an important element to move towards the actual human AI collaboration. And the second part we'd like to add is more adaptive elements. So once a human actually said, okay, this prediction is true or this prediction is false, we of course want the model to take this into account for the future, so the model gets better and adapts to the new knowledge as a human user interacts with it. And with this, there is one final outlook here that I want to share with you of what basically we hope the final goal can be. And this is again for the task of polypharmacy side effect prediction, where we hope that if we can move towards true human AI collaboration, we can have a biomedical researcher that can interact with the AI system to more effectively solve this task. So let's assume we have a biomedical researcher and they ask, what happens if someone takes paliperidone and calcium? And on the other side, we have the AI system, which will tell us it will cause pain. And this would have been the original step 1 with the knowledge graph embeddings and no explanations. But of course, the biomedical researcher will want to know why. And here with gradient rollback and also with explore and explain, we can tell the biomedical researcher that the model thinks so because paliperidone interacts with MMP2 and calcium interacts with LPAR1. And of course, for a true collaboration, we need an interactive element, and this will go on by, for example, the biomedical researcher asking, but what do MMP2 and LPAR1 have in common? And this is also here where we hope to extend explore and explain with an interactive component, and with the hope that the model might be able to say something like MMP2 and LPAR1 will upregulate each other. And another question a biomedical researcher might want to ask is if the model has seen a similar case before. And here we hope that to add a component where the model can then reply, yes, I've seen the same two pattern where this kind of upregulation and connection caused pain before. And then based on this, the biomedical researcher will have a very promising combination to try out, and they can go and verify this, and then either agree that this is indeed a side effect or maybe that it was not a side effect. But an important part here is that whatever the final conclusion is, that the biomedical researcher will be able to tell the model, for example, yes, this was right, and that the model will then add this to the knowledge base and actually adapt based on this. So to summarize, the talk today had three parts. First, we had a brief look at what knowledge graph embeddings are and how they can be used to infer new knowledge. And then we looked at gradient rollback, which allows us to explain the predictions returned from knowledge graph embeddings. And then we looked at explore and explain, which is an interface to interactively explore explanations, and with which we hope to move closer towards human and AI collaboration. And with this, thank you for your attention, and I'm happy to answer questions.
Okay, great. Thank you very much for the presentation. Are there any questions?
I have a question. Firstly, thank you so much, Caroline, for the great talk. So about the gradient rollback approach, considering that this model is actually quite old scoring function, I have two questions. Firstly, how hard it is to extend the gradient rollback to other more complex scoring function, and I'm wondering if you have done any experiments on those kind of newer scoring function, like rotate E or conv or any other more newer or better approaches.
Yes, so it's definitely possible to extend this. We've only explored it apart from this one with complex so far, but there is no reason why you can't apply it to other scoring functions. It could get a bit more complicated if you try to use it for completely different models, say a transformer, because gradient rollback has to basically, for every time you have a training example, remember the change in the parameters. So if the number of parameters that are touched in each training step is large, then also the amount of memory you need would be large. But for scoring functions, as long as the dimensions is not really huge, it'll be possible to use them.
Okay, great. Did that answer your question?
Yeah, that was great.
Okay. Great. Are there any other questions?
Actually, I have one more question. So I'm wondering, in computational complexity wise, how it is comparable, the gradient rollback, to some more complex approach, like using influence function on top of a knowledge graph, because those methods are very, very expensive regarding computational complexity. So can you comment on that, please?
Yeah, so basically every time you have a triple, you just need to, like, the computation itself for the gradient you do anyway, right? So you just need to remember what this was and basically write this down. So as long as the dimension, I mean, it relates to the previous point. So as long as the dimension isn't too big, it's not an issue.
All right, okay. Any more questions? Then I guess we could move on to the next item of the agenda. Okay, thanks again, Caroline. It was very interesting.
Yeah, thank you for having me.
Thank you so much, Mathias and Caroline, for the great talk. Next, we will have our first contributor talk. Jipei Wei is a graduate student from Jilin University. He received his bachelor degree in computer science from GLU as well. His work is focusing on designing deep learning models for knowledge acquisition from text resources and develop knowledge-enhanced system for reasoning and decision-making. Jipe, please take it from here.
Okay, thank you. So can you see my screen?
Yes, go ahead.
Okay. Well, hello everyone. My name is Zhipei Wei, and I'm a master's student from Jilin University. I'm very glad to share our ongoing work where we introduce a general framework, namely cognitive knowledge graph, trying to unify symbolic and continuous knowledge representations for machine reasoning. And by the way, if you have any questions during the presentation, you can write it in the chat box and I will read it for the audience and answer it after the presentation. So this presentation will go over the following 4 parts, including background and problem definition, proposed method, and conclusion. So let's start with the background. Well, symbolic reasoning methods such as expert systems are believed to be reliable and interpretable in solving inference problems of specialized domains. But however, these rule-based methods are difficult to generalize because obtaining a comprehensive set of rules from human experts is costly and time-consuming. And recently, continuous knowledge representation models utilize the distributed representation of a knowledge graph for machine reasoning tasks, such as knowledge graph completion, in which the models could generalize from known facts to unknown or unseen facts, but probably true facts. However, such models can only represent and reason about multi-relational data in the form of triples instead of if-then rules that represents logical consequence and thus has limited interpretability. So our motivation is that can we unify symbolic and continuous knowledge representation techniques to perform complex inference tasks? To answer the general question, we have to firstly find the solutions for the following 2 questions. The first one is how to combine the rules and the knowledge graph, and what will we get by doing this? But before answering the first question, I'd like to first answer the second question instead. That is, what kind of complex inference problem we are concerned in this work? So in this work, we introduce a novel task, reasoning task, namely the cognitive inference problem, with a large-scale knowledge graph and a moderate set of if-then rules as preliminaries. We focus on such situations where observation leads to conclusion based on the cognitive knowledge, which is essentially different from the traditional KG inference problems, such as linked prediction. To solve the above problem, we first introduced the cognitive knowledge graph, namely CogKG, and then develop a reasoning inference paradigm based and it takes expert rules and logic. So obviously, so let's after answering the above motivation to use CogKG give rise to the novel reasoning paradigm based on workflow of the
I'm sorry to interrupt you. Are you hearing me?
First, we perform
Niepert, sorry. Your internet
obtain the
your internet is not as stable.
any sound problem.
Niepert, can you hear me? Niepert?
Shall we go on?
Okay. So we didn't hear anything from slide 7.
Knowledge representation learning.
Can you hear me? Oh God.
Oh,
These are the problems with
from the so first introduce the cognition, then develop a reasoning called KG is a graph expert rules in a unified entities as nodes as edges. First question could be
yeah, JP, can you please turn off your video so you might get a better connection? Just turn off your video. Your voice is just it's shattered. We cannot follow you. Yeah, sorry everyone. You guys probably had similar experiences during COVID pandemic. This is what happens when you have Zoom workshop. I'm thinking he's trying to reconnect. We might be able to wait for a few more minutes before moving to next invited contributor talk. But let's see if he's here. Maybe we can wait a few minutes for Xiangpei to see if will join us again. He's not here yet. Okay, maybe we can move on to the next contributor talk. And if he will come back, we try to ask him to redo his presentation. So our next contributor talk is Xiangyu Peng, who is a PhD student at Georgia Tech. She received her master's degree in structural engineering from Stanford University. Her research is focused on the intersection of reinforcement learning and NLP. By that, I ask Xiangyu to join me here. The stage is yours.
Hi, could you guys hear me? And this is my screen.
Yeah, you can.
Oh, great. Oh, hi, everyone. This is Xiangyu, a PhD student at Georgia Tech. And today I will present our ongoing work, Explainable Reinforcement Learning Agents with Stacked Hierarchical Graph Attention. This work is done by me and the graduate PhD student Raj and our advisor Mark Riddell. And we are from the Entertainment Intelligence Lab at Georgia Tech. So nowadays, when we see the agent and when we see like the AI stuff or the robots, when they move, make decisions, and we're thinking about like, what are they doing? And are they doing some arbitrary actions? Is that possible? Like this agent can explain themselves and tell us like why he or she is doing this. So if the agent can explain themselves, it would be great. So this is our motivation. So we hope that we can make these AI agents, the reinforcement learning agents, think out loud. So now, like, if they can do this, like, it can improve the trust a lot. So that's why we do the explainable AI in this project. We do the artificial intelligence methods and techniques, which can provide the human understandable insights into how and why an AI system choose this action or make this moves. So before like training an agent, so we need to define like what kind of environment we want to use. So we hope like we want to train an agent in an event like which it can provide a wide set of scenarios. So it can like explain itself, like when it's reasonable, go through it. And of course, like for the humans, like when we explain ourselves, like most of the time we just use natural language. So that's why like we hope we can have an environment which have a lot of natural language thing. So that's why we go to the interactive fiction games. This kind of game is with the real human written natural language. So this is a great test bed because we can collect a lot of natural language data. And at the same time, we can link the game states and actions to their corresponding natural language explanations. So when we think about what is interactive fiction games, let's take example. We can use the Zork one, which is a game like every time you see some natural language observations, it will tell you, okay, you're standing in an open field of a White House, and there is a small mailbox here. And then like the environment will ask you, the player or the agent, what do you want to do? And the green letters are the actions I took. It's like, okay, I want to open the mailbox. And then like, what will happen? The environment will tell you, okay, after you open this mailbox, you can see a leaflet. So this is, and then this is interactive with the environment. And then you can take more actions. So the designer designed this kind of game based on this kind of hidden map. The player doesn't know anything about this map. They only see the natural language observations. However, their goal is like, they want to explore the world, go to different rooms, collect the different objects, and get a score. So when the agent play this game, so for example, open the mailbox. So what we want agent to do, we hope like it can explain itself. For example, here, the agent want to open a mailbox. I hope this agent can tell me, okay, I open this mailbox because I see a mailbox and this mailbox is openable. So that's why I want to open the mailbox. So we hope like when the agent make a decision, it can explain themselves. So we have two goals in our projects. The first, we hope the agent can explain the step-by-step actions. The agent can tell me why I do this decision. And then after like several rounds of games or after the whole game, I hope like the agent can tell me, can summarize the high-level trajectories. So first, let us take a deeper look on how to explain themselves. So when we train a reinforcement learning agent to play this kind of interactive fiction games, at the same time, the agent learns to build a knowledge graph based on the observations. So we can see here is like, okay, every time when the agent sees some natural language, it will build a larger and a larger knowledge graph. This is something like the agent learns from the word. So it builds a word, represents the states as a knowledge graph triples. And then like with the game and like the agent will build a larger and larger one. So here we use Albert QA with fine-tuning, and then like every time when the agent see the natural language thing, it will ask a question like, where am I? What do I have? Something like this. And then we build a knowledge graph based on those. After we have so when we have the knowledge graph, actually what we want to do is like, we hope like when the agent play this game and we want to find like, okay, which part of the knowledge graph is the most important. And then like it will tell us like, which triples is most important for making these decisions. So that's why like we design 4 sub-knowledge graphs. The first, we'll consider like the attributes of the objects. So for example, here's like when you do some action like take the egg. So if the egg is openable, so it will be very important for making this decision, right? So that's why like we consider the attributes of the objects and also the objects the player has, because the player only can interact with something they have, or they can interact with something which already in the room. And then we also consider some other informations. For example, when the player wants to go east, it says like, okay, because in the knowledge graph, we see like in the east of the behind house is a forest. So it kind of explains why the agent wants to go east. So these are the 4 sub-knowledge graph we have. So this is our pipeline, the architecture. We have the natural language observations. It will go through the LSTM attention, and we also have the full knowledge graph. The knowledge graph the agent built, and go to the graph attention network. And we also have 4 sub-knowledge graphs, which is we talk about in the previous slide. It's like we want these 4 subgraphs and go to the hierarchical attention, and then like go to the A to C agent to make a decision. So these 4 subgraphs will go to the graph attention, and then like we will rate the attention values, because we believe like the attention values are used to capture the importance of the KG triples. So when we get a high attention value, we think these triples are very important for making these decisions. So we have an end-to-end A to C model. So we put the natural language observations in, we put the knowledge graph triples in, and the sub-knowledge graphs into the end-to-end A to C model. It will output actions and credit value. The credit value is used to find the actions which kind of like maximum the long-term expected rewards. And when we have this architecture, before I introduce the examples here, let's see what we use as a baseline, what we compare our model with. So if we don't use any knowledge graph, this will be our baseline. So we only put the natural language observations in, go to the attention, and then like go to the A to C model. So the baseline is no knowledge graph at all, and we only use the attention of text observations to find the most important words. And for these important words, we hope these words can emphasize like when the agent rated this observation, why he makes this decision. Let's see some examples. So in this game, when you see like, okay, I'm behind the White House and there's a small window there. So when the agent tell me, okay, I want to open the window. So if there's no knowledge graph, the baseline, it will say, okay, the behind, corner, and house, these 3 words are very important. That's why I make the decision. However, from our architecture, it will tell you these 2 knowledge graph triples are very important. Window, behind house, relationship is in. Window, interactable, relationship is. Another example, I'm in the forest. So the agent said, you can go around the forest. And from the baseline, it says this will seem like doesn't look like makes sense. And like from architecture, it tell you, okay, because the tree is interactable, relationship is, trees, forest, relationship is in. So that's why like I want to make a decision. We can see here, because when we see the knowledge graph, we have the nodes, we have the relationships, we have another node. So it's very easy to do the verbalization. It means like I can translate the window, behind house, relationship is in as window is in behind house, or window is interactable very easily. So that's why like after we extract the most important KG triples, we go to something called the verbalization. When we have the observation, we have the actions, and we will just translate it into natural language, human understandable stuff. It's like, okay, I want to take an egg because nest and egg are interactable. So this is the explanation our agent will give you when the agent make a decision. So after talking about like explain the step-by-step actions, the second thing we do is to summarize the high-level trajectories. Let's see example of the log. So this is something like when we run the agent. So when the agent like go through the word and play this game, for every step, we will save all the logs. So we will say what's the observations, what's the actions, and like the reward is blah, blah, and what's the explanation I can give you, or the critic value and scores. So every time when we see a critic value is very high, we think the state or this action is kind of give you a high reward. So that's why like we will save all these logs, and we will save like, we will summarize the whole game with these states with a high critic value. And then it can help us to find a subset of tasks by the critic value. And also like after I gave you the summarization, you can walk through these states and you will think, okay, these states are more likely to give me a high reward. So these are the tasks, like if I want to get the score, or if I want to play this game, what should I do first? So let's take example. So example here is like, I want to take the egg. And this is from my experience. From the kitchen to take the egg, what should I do? Actually go east first, go north, and collect the tree. So this is never used for training a data. So this is only something I want to show here, just example. And then like from our model, it will tell you, okay, these are the most important actions and states I extracted from the logs. We can see here, okay, you should go east first because window is in the kitchen, and then you can go to behind house. And there are several states. Then like you find, okay, another important thing is like you should go around forest and then go to the forest path. And then you should go up the tree because trees is in the first path. And then you can take an egg because blah, blah, blah. So it will tell you like what's the most important task here. We find this by the high value of the actions based on the learned value functions by the critic. So because of this ongoing work, so what's the next step? So before we have already generated like the all the explanations, logs, and so we need to verify like this is definitely better than the baseline without knowledge graph through the human study. So first we need a verification, and the second one, we need to extend our model to more scenarios. Not only like more games, like we choose like the Zork one, they're here, and we should like choose much more games so we can have more scenarios and make sure like it works for all the games or all the scenarios. And the takeaway today is like, when we think about how to like make the agent or reinforcement learning agent or any AI agent to explain themselves. So this is a good way, like when we build it, we can involve the knowledge graph in, and by seriously design the knowledge graph, it could help us to find like, okay, which triples are most important. So when you guys like think about like explain the reinforcement learning, maybe it's a very interesting way to do that. Just involve the KG and then you find the most important triples and then ask it to explain it for you. And also like we also find like, okay, when the critical value is very high and like after the whole game, you might think, okay, this is the most important task you want to do. So it can help you summarize the trajectories. It could also like help the players or help the designers to summarize the most important thing. Thank you. Any questions?
Thank you, Xiangyu, for the great talk. Actually, we are a little bit short on time. Does anyone have any question? If not, I can ask some question myself. So, because that you introduced graph attention network to add explainability to your framework, basically I have a question. Firstly, I'm wondering how introducing graph attention affect your agent performance. And secondly, since it is a known fact that graph neural network has a very high computational complexity, I'm wondering how this affects your overall framework as well. Can you comment on that?
Okay, so for the first, could you please clarify a little bit for the first question? I got a little bit confused about it.
I mean, the accuracy of the agent itself to solve the task, not explaining. So yeah, you have this evaluation study here comparing.
Oh, yeah, gotcha. You mean like we didn't show like how fast or how many scores like this kind of agent can. Okay, yeah. Actually, let me show this. So this work is based on one model called Qbert, and like which is done by the PhD student in our lab. And we didn't introduce here is because we have proved like this one can definitely like reach that one's performance, and that one is state of art. So because this is not like the biggest contribution here, so that's why like we introduce the performance, but it's definitely like can catch that one. Yeah.
Great. Thank you for your answer. And again, thank you for your amazing talk. I think we don't have any other question, and actually we are short on time. So thanks again. And we have GP joining us again. So I'm asking him to join me here and start to continue his presentation from slide 7, if it is possible for him.
Well, I'm sorry for the bad connection. Well, you know, I'm in China and my VPN doesn't work well at the midnight. So I will share my screen again and start from where it stopped. So is slide 7? Okay. So we just introduced the cognitive inference problem, and to solve the above problem, we first introduced the cognitive knowledge graph, namely CogKG, and then develop a reasoning inference diagram paradigm based on it. Briefly speaking, CogKG is a graph that expresses relational facts and expert rules in a unified framework, and it takes expert rules and entities as nodes and the semantic relationship or logical consequence between nodes as edges. So obviously, a possible answer to the first question could be CogKG. Now let's back to the motivation. So after answering the above 2 questions, we can now convert the general motivation to a more practical challenge. That is how to use CogKG solve the cognitive inference problem. And this gives rise to the CogInfer, which is a novel reasoning paradigm based on CogKG. Well, here I will briefly introduce the workflow of the CogInfer. First, we perform knowledge representation learning on the CogKG and obtain the distributed representations of nodes and edges. And then for each observation or query queue, we create a corresponding infograph by iteratively identifying the closure of the involved rule nodes and entity nodes. The infograph is a subgraph of the background CogKG, where the entity nodes in this graph are particularly categorized into 2 sets, namely a known entity set and an unknown entity set. Lastly, we perform reasoning on the infograph through applying expert rules or link prediction with the learned distributed representations to predict the unknown entities in the infograph, and reports the conclusions with certain relational triples or rules at the decision path. So in summary, in terms of contribution, we first introduce a new challenging machine reasoning task, which is cognitive inference problem. And then to solve the problem, we propose CogKG and CogInfer that unifies the symbolic and continuous knowledge representations for machine reasoning. And since this is ongoing work, we are still working on several important parts like data collection, cognitive knowledge graph construction, and practical implementation of the CogInfer framework. So thanks for your attention. If you are interested in our work, please, you can scan the QR code to learn more, and you're more than welcome to contact me for further discussion. Thank you.
Thank you so much for the great talk. Is there any question? If not, I can ask some question myself. So considering that you assumed that you have access to this set of node rules to combine it with your knowledge graph embedding, so basically I have 2 questions. firstly, I'm wondering if you put any limitation on the rules that you have. Is there supposed to be less than 2 hops rules, or there's no limitation on the rules?
Yeah. Okay, I understand. For the rules, currently, okay, I will put it in like the rules. We have some premise, like some conditions. If we are doing some clinical diagnosis, and the conclusion of the rules, we only focus on that. The rule only leads to one node instead of multiple nodes, like a set of empty nodes. Currently, we are unable to model the many-to-many rules, but we only focus on the many-to-one rules. Like we have many symptoms to one disease instead of to more than 2 disease.
I see.
Okay.
Yeah, it kind of addressed my question. Okay, let's go to the second question that I have. I'm not sure if you are familiar with GPT-3 approaches, but again, it's some kind of open-ended question that I have. So again, assuming that you have access to these rules and you want to find this missing entity using the rules and your combination of your rules and your embedding approach, I'm wondering if we can define this problem as some kind of prompt designing in a careful way, and then feed the prompt to the GPT-3 and ask GPT-3 try to predict the missing entity or complete the knowledge graph for us.
Well, actually, it's an open question, and we try to formalize the problem by doing some mathematics, and in this current stage, we haven't formalized one like a formal problem definition, but we only have an abstract of our general ideas.
I see. Yeah, that was I know it was just an open question.
Yeah.
It would be interesting. So this GPT-3 approach.
Yeah, but we will work on that.
Yeah, because recently the few-shot learning aspect of NLP become very widespread, and recent work try to adopt those approaches to knowledge graph embedding and exponential knowledge graph as well. So I was just wondering if it is applicable to start using GPT-3 itself and just be a little bit careful and more smart about designing prompts and ask GPT-3 to solve this task for us. Again, thank you so much for your amazing talk. I think we are right out of time for our break. So we go on a break for 15 minutes, and I will see you all in 15 minutes for the second section of our workshop. Thank you so much.
Okay, thank you.
Well, hello again, and thank you for staying with us. Let's start our second section of XGML workshop. I'm super excited to introduce our next speaker. Marika Zitnik is a professor of biomedical informatics from Harvard Medical School. Prior to joining Harvard, she was a postdoctoral fellow in computer science at Stanford University. Her research is mostly about investigating machine learning for science and medicine, infusing biomedical knowledge into deep learnings. Problems she investigates motivated by network biology, medicine, genomics, drug discovery, and health. She won many awards pursuing her research, such as Next Generation Biomedicine, Joseph Staffen Golden Medal, and many best paper awards. Marika, thank you for joining us, and the stage is all yours.
Hello, everyone. Thank you for this kind introduction. I'm delighted to be here with you today and talk about explainable graph AI for drug discovery. I hope you can see my screen and the slides there.
Yes.
Great. Okay, so the code and the papers, the data set that I will be referring to today are all publicly available and can be downloaded from our lab website, zitniklab.hms.harvard.edu, where you can also find more information about the projects we have in the lab. Okay, so given that this is a CS/ML workshop and conference, a good question to start with would be, well, what is drug discovery and why do we care about drug discovery and why particularly it's relevant for explainable AI and graph AI? And so I will start with that question. So drug discovery and development refers to a very lengthy, resource-intensive process through which new drugs get developed and eventually approved by the regulatory agencies and then put on the market for patient use. That is a process that takes on average 12 to 16 years to design a new drug from scratch and deliver it to the market. It can cost between $1 to $2 billion for one drug. And why is it so resource intensive? Why it takes so long? Because it has very high failure rate, meaning that the entire process consists of multiple steps or phases. And in each of those phases, there are certain properties and characteristics that a candidate drug needs to have in order to completely successfully complete that stage and progress to the next phase of drug discovery development. And so that means that even though we might start with a large number, actually tens of thousands of chemical compounds that initially seem promising as they might be safe and effective for treatment of a particular disease, through the funnel of different stages of drug discovery and development, we might later realize that compounds that were initially promising are really not promising because they're not safe for humans, or they don't really work the way they were intended to work. And if that happens, then we are left with smaller and smaller number of candidate drugs. And if we are very lucky, then eventually there is at least one drug and one compound that goes through that entire process that is safe and effective and can be approved for use in patients. If not, there is likely that the entire process fails and there's lots of money and resources that have been wasted. And so, as you can imagine, because this process is so lengthy and it's so expensive and resource intensive, there's a great need and many opportunities for how AI, automation, novel data resources can help us expedite discovery of safe and effective therapeutics. Why is now AI for drug discovery so challenging? So what are some of the fundamental challenges that need to be solved in order to really realize that vision of how AI can automate science of drug discovery? And why is that a very nice, interesting domain for machine learning scientists for developing new algorithms? There are a variety of reasons, and I will mention 3 of them today that I will also address in the rest of the talk. So the first reason is that in order to be able to predict whether a particular drug will be safe for a patient and will also effectively treat the disease that the patient has, we need to rely on a variety of different kinds of data. So there is a need to integrate heterogeneous confounded data sets that span from molecules all the way to the level of interactions between individuals in a society. So in order to really make accurate predictions, we really need to integrate information from genes all the way to behaviors of a patient. We need to be able to have a unified mathematical representation of these multi-scale data sets in order to be able to capture the complexity of a phenomenon such as a disease or a drug. And so naturally, that means that networks or graphs, which have been covered extensively at this conference, are an elegant universal mathematical representation for drug discovery. It's important that we're able to translate those predictions into actionable hypotheses, meaning that there is a realistic chance and a realistic way to take predictions made by machines, by predictive models, and use them to inform drug discovery process. And so what I mean by that is that decisions that are made during the entire process of drug discovery and development are often very important decisions. Sometimes they are life and death decisions, whether a patient will be involved in a clinical trial, can participate in a clinical trial or not. And if an incorrect decision is made there, it might lead to very bad consequences for the patient, either because they should be enrolled in a trial and the drug might work for them and they would be healthy, or if they are enrolled in clinical trial but they shouldn't not be, they might experience unwanted adverse events. Furthermore, important decisions that are made by human experts here relate to, well, which of those 10,000 compounds that initially seem promising should be put in the second and the third and stage of drug discovery and development. So how should we allocate limited resources to kind of maximize the yield of the discovery process? So this kind of, because of these important decisions that are made, it's important that our algorithms are robust, that we can somewhat ensure that the models behave responsibly, and that there are appropriate checks and balances built into the deployment or practical implementations of that models. As a result, it means that accuracy is no longer sufficient consideration when we are developing new algorithms, and there are other criteria that are important. In particular, those that I will focus on today relates to making sure that our predictions can be understood and interpreted by users of ML models in a meaningful way. And third challenge why AI for drug discovery is particularly hard is that fundamentally discovery of drugs and development relates to really pushing forward the frontier of science. So by definition, we are developing new drugs or modeling new diseases and there is very little information available about them. So that means that there is very little, if any, labeled information available that one can use for supervised training of the models. That is challenging because many of recent breakthroughs in AI depend on having lots of labeled data. But when we are developing a new drug in development, there is very little labeled data available about the drug. Of course, we don't know if the drug will work, and it might be a completely different kind of pharmaceutical modality than drugs that are on the market. So it's not easy to be able to predict whether that drug will be safe for patients if the only data we have is the data about that drug safety in model organisms like mouse or some other or some other model system. And so these three challenges, when put together, present unique, exciting machine learning challenges and opportunities for advancing algorithms. And so I will describe some of those advances in this talk today. So the plan is that first I will talk about and I will formulate the problem of identifying effective and safe therapeutics or cures for emerging diseases, and outline recent algorithms that we developed for tackling challenges that come with that. In particular, that will be few-shot learning on graphs and our work on explainable graph AI. And second, I will very briefly outline Therapeutics Data Commons, which is our open science initiative with AI-ready data sets and many different kinds of graph modalities that were particularly designed in such a way that they're ready for use by machine learning scientists who would want to test and evaluate their algorithms on problems related to drug discovery. Okay, let's begin with the first topic for today's talk. So the first topic, or the motivation for the first topic is the fact that that when we are concerned with the development of new drugs, it's very challenging because that fundamentally requires generalizing to a particular new phenomenon or a new disease that one want to develop drug for. And so prevailing graph machine learning models require abundant label information for that. But labeled examples are typically very scarce. Where we are more concerned with a new disease or an emerging pathogen, for example, COVID-19 in the year 2020, that at that time was never before seen disease, right? So for obvious reasons, that was a new disease where no data was available, no example of approved treatment. So there was no way to train a supervised model to identify what might work, what treatment might work for COVID-19. And so visually, that the challenge here is that prevailing methods for graph representation learning assume that what we have is we have these graphs that are already richly annotated and labeled, and we can use those labels effectively through neural message passing schemes, propagating that label information to make predictions for remaining unlabeled nodes in this graph. But what happens in real world, where we go outside of academic benchmarks, is that the data that we see are looks more similar to what I'm showing in the right part of the slide. We have these vast networks, and most of the nodes, most of the entities in those graphs are unlabeled. They are dark matter for the algorithms. And what the only thing we have is a handful of labels that we can leverage in order to make predictions. Okay, so the paradigm to use to tackle this particular problem is few-shot learning. What I will outline next is an algorithm that we developed for few-shot learning on graphs and published at Rdfs last year. It's called the GMeta. And before I go into details in the algorithm, just one single slide on background for few-shot learning, more for the reason so that we are all on the same page regarding terminology. So the background here is that few-shot learning is a particular instantiation of meta-learning, which is a broader area of research in the field of supervised learning. It is concerned with the fact of how to train successfully classifiers where only a few handful of labeled examples called shots are available for training the model. In particular, when we will use the word k-shot and class classification, that is a situation where we are concerned with training a classifier that will that can classify objects into n classes, and for each of those n classes, there are only k shots or k labeled examples available. So here's one example shown in the slide, which just is done for the imaging modality. And so few-shot learning consists of typically two stages. First stage is called meta training. In the meta training stage, one would design a large number of training tasks. Each training task would be specifically designed such that it's challenging for the model, in the sense that there are only a handful of labeled examples in the support set that the model can use to train a supervised model. In this example, we can see training task 1 would require training a classifier that distinguishes between 3 classes, and for each of those 3 classes, just 2 labeled examples are given. And then training task 2 would be of similar structure, but for 3 different classes. And the hope is that, well, by specifying a large number of training tasks, and we can capture the nature of that particular problem, and train our few-shot learning model in such a way that it will very quickly adapt to a new training task. And we want to do that because at the testing phase, we will be presented at the test task that will also have very few labeled examples, and the model, if will be able to very quickly adapt to that task because it was trained in such a way that can quickly adapt to new classes. So imagine here in this at the test time, we would need to build a classifier that would distinguish between ducks, dolphins, and chickens. However, we would only have 2 labeled examples for each class, but that is possible to do with few shot learning strategies. So next, while we are not interested in modeling images in this talk, we really want to do few shot learning for graph structure data rather than imaging. And so that has motivated us to develop an algorithm that we refer to as GMeta algorithm. It was published at NeurIPS last year, and the details and lots of empirical tests are in this paper called Graph Meta Learning via Local Subgraphs. The problem formulation for GMeta is the following. Imagine that we have a single graph, and the test that an ML test that we're interested in is node labeling. In this class, we might have different kinds of labels. So in this particular example, we have yellow, different shades of yellow labels and different shades of blue labels. So in this particular case, the situation is that we want to have a graph meta learner or few shot learning model that will be able that during training time, meta training time, it will only see different shades of yellow label, and in the meta testing phase, that classifier will very quickly be able to also make useful predictions for blue labels, even though there might be just 1, or in this case 2 nodes that have a blue label set. This is just one particular formulation in which GMeta can be used, and it's formulation where the learning task is defined on a single graph. GMeta can be used for other settings where we don't have one graph, but we have a large number of different graphs that we want to learn over, such as graph classification tasks. I will not go into details there, but these details are all covered in this paper. So visually, the way the key idea here is that we adopt the same strategy in the sense that we have 2 phases for training our GMeta models. In the meta training phase, we define a large number of tasks. Each training task is defined with training a node classifier that is sampled based that is sampled and defined on the nodes that have the training label set Y. And then in the meta testing phase, we ask the model to generalize to this new label set Y star that has not been seen in the training phase. So the meta test time, we are building this classifier that can distinguish between dark blue and light blue labels. And we can do that with just having, in this case, 2 labeled examples, 2 nodes that have a particular label for each of the 3 distinct label types. And so that is what GMeta can do. What is the key idea of that allows us to train node classifiers with so few labeled examples? The key idea is that the GMeta relies on local subgraphs to derive a signature function that describes each and every task, both meta training tasks and meta test tasks. So the idea is that we have us input this the graph and with a small number of labeled examples. So around every labeled example, we can look at the structure of enclosing subgraphs, and we look at the set of enclosing subgraphs for that small number of labeled examples that we have. We use that information to learn a subgraph signature function that can effectively describes a distribution over enclosing subgraphs around labeled examples. We can map that subgraph signature function to effectively initialize a new task. And the way that subgraph signature function process of learning is done is through this particular function f that is a neural message passing scheme. That can be a variety of different kinds of neural message passing architectures, including, for example, graph isomorphism network, jumping knowledge networks, various attention mechanisms, depending on the particular application you would want to use. But the key idea is that we use subgraph signature functions to transfer information from one test to the other. This is in sharp contrast with some of the meta-learning work in other data modalities outside of graphs that were particularly concerned with learning signature functions for tests based on the entire data set, which would mean that we would be learning functions based on the entire graph. This is something we don't want to do because it is really not scalable. And so we show that subgraphs are, if using these subgraph signature functions, not only makes the algorithm very scalable, much more scalable than learning signature functions for entire graphs, but it also it's possible to show that we don't lose much of information by limiting ourselves to enclosing subgraphs of target nodes. In particular, we show in the paper that we can analyze what is the influence of one particular node in the graph on the target node that we want to make prediction for. And in predominant message passing networks, that influence decays exponentially as we go further away from the target node. And the implication of that is that local subgraphs around target nodes contain most of the relevant information and that effectively means that working with subgraphs is both computationally efficient as well as efficient from the informational standpoint. Conceptually, you might we can understand and reason about the value of subgraphs for few-shot learning in the following manner. So we typically in graph neural networks, we consider fundamentally two different kinds of information that can be leveraged by GNN architectures. And so the first kind of information relates to label propagation. In many cases, we make the GNNs make assumptions, and this is supported by kind of classic network science work, that nodes with the same label will be nearby in the graph. They might be direct neighbors, or they might be in the network vicinity of each other. And so effectively, that means that various schemes that propagate labels across edges of the graph can be a useful way for node labeling. The other notion is structural similarity, which is completely complementary to label propagation. And it says that nodes with the same label might not be close to each other in the graph, but they would have a similar structure in their local neighborhoods, even though they might be very far away from each other, many hops away from each other. So the reason here is that when we have settings where the label information is scarce, then we cannot solely rely on label propagation. Label propagation is not sufficient, and because it's very challenging to reliably propagate labels through the entire graph that might have thousands or tens of thousands or millions of nodes, and we just have a handful of labeled examples. And in those situations, we need to better leverage structural similarity. And that's exactly what the GMeta does with the use of local subgraphs and the learning of local signature functions. So that allows GMeta to reliably make predictions even when the amount of labeled information is very small. Okay, so now that I outlined GMeta algorithm, I will show you how we can practically implement and deploy the algorithm in an important application in drug discovery. And then I will also talk about how XAI has fueled discoveries in that application. And so the motivation for this application is the need for rapid therapeutic innovation with the effort of the goal of accelerating the discovery of safe and effective therapeutics. The project that I will outline happened at the core part of it occurred at the beginning of pandemics last year. So it's not hard to realize that pandemics demand safe and effective therapies developed at unprecedented speed. If you remember, in my introductory slide, I mentioned how it can take 11 to 16 years on average to develop a new drug from scratch. Of course, that it's not really useful or it's not useful at all, or when we are faced with a pandemic or public health emergency. This traditional iterative development, experimental clinical testing, and approval of new drugs is simply not feasible in those situations. So the challenge was, how can we compress, or can we even compress years of work into months or even weeks through the use of AI and automation and new data resources? So I will describe a project that took place between March 23rd last year and June 15th last year. So that is just 3 months time. And during that 3 months time, our team and collaborators who were medical experts, virologists, and biologists were able to implement the entire drug discovery pipeline by relying on available data sources, implementing and running GMeta algorithms to identify possible therapeutic opportunities for COVID-19 patients, and then really take those predictions and experimentally validate them in biological laboratories and see whether we can make sense of them. So I'll spend the next 2 minutes outlining that study, and details are also described in that with all the data sets and everything in this PNAS paper, which we published earlier this year. The core machine learning task that we will be solving in this project is answering the question of what drug might treat what disease. So in particular, we are interested in having a model that can predict, given a particular compound, a particular chemical structure, what are the diseases that compound might treat, meaning it would successfully improve the health state of patients with that disease, and it would also be safe for patients, right? So it needs to treat the disease and also be safe for patients, not toxic or lead to some adverse events. Now, in order to answer that question and make predictions we need to understand how drugs work, meaning that we need to have information about when a drug is taken by a patient, what happens in the body. So effectively, that means that we need to represent the data with some large network knowledge, in particular case, knowledge network data representation. And in our case, what we will do is we'll have all the currently approved drugs in the US represented as nodes. They will link them to the proteins that are in human body, and in an effort to model how those drugs, when they are taken, what are the proteins whose activity are changed in the human body, is changed in the human body after the drugs are taken, how those proteins interact with each other, and then actually exert their effect on the disease that patients have. And so a bit more details into that is next. That one I want to discuss. And so in particular, in March 2020, when this project started, there was very little information available about COVID-19. The only information that was available was information about when a person has COVID-19, what are the proteins that are in the human body, so these worker molecules that are in human cells that the virus attacks. And so in particular, it was the data generated by our collaborators from UCSF revealed that there are 332 human proteins that the virus attacks. And those proteins, because they're attacked by the virus, they cannot work as they were intended to work in human body, and that can lead to the onset of the disease. So we represent those 332 proteins as a module or a subgraph of the protein-protein interaction network. So what we have is a graph of where every node is a protein. Proteins are connected based on whether they physically interact with each other in the human cell. And out of all the proteins that are in human body, we know which are those 332 that the virus attacks. And we can use a subgraph on those, and that is our viral disease module. We can do the same for each and every drug that is approved on the US market by saying, well, we will define drug by a subgraph or a module of proteins that the drugs target when it's taken by the patient. And so Now, implementing that idea, not just for COVID-19 and a particular drug, but across the entire range of approved drugs and human diseases, gives us a COVID-19 repurposing knowledge graph. The way to think of it is that this is a knowledge graph that has human protein interaction graph as a backbone. On top of that human protein interaction graph, we overlay those drug modules, one module for each and every approved drug in the US. And we overlay disease modules, one module for each and every common disease that has some treatments. And also there is one module that represents COVID-19 disease. Okay, with that data representation, the task becomes that given common diseases and given treatments for them. So we can look at what are existing treatments for cancer, what are existing treatments for other infectious diseases. Given all that information, we want to identify what might be candidate treatments for COVID-19. Of course, for COVID-19, there were no examples of successful treatments, so that's a zero-shot learning problem. And essentially, it means we can use GMeta in the following manner, that in the meta training phase, we design a large number of training tasks. Each training task is concerned with predicting diseases, predicting drugs that can treat one particular disease. Disease 1. In training task, we are training the model to predict treatments for disease 2, and so on and so on. And we're doing that in an effort that at the test time, we then use the model in a zero-shot manner to prioritize and predict candidate treatments that might be effective for COVID-19 patients. And so that is how GMeta is used to identify a prioritized list of drugs that represent therapeutic opportunities for COVID-19. Given that prioritized list of predicted drugs, we first wanted to understand, well, how good are those predictions? But the question is, well, how can we calculate the quality and accuracy of those predictions if there are no ground truth data available? Okay, so what we came up with is, well, we used proxy information, so not really gold standard data, but perhaps bronze standard information, which was we looked at what are drugs that were at the clinical trials at that time. And we asked whether, because some drugs were investigated in clinical trials for COVID-19, meaning that medical community thought that they might be promising for COVID-19 patients. So where are those drugs in our predicted list of drugs? And we compared GMeta approach to a variety of other network science, graph neural network techniques, and we found that GMeta performed much better and was much better at identifying what are those drugs that were also that the medical community thought might be promising. But of course, that's not really kind of true evaluation of the quality of the model. And our goal here in the project was really to see to what extent can these graph neural network models practically advance the discovery process. So we teamed up with National Emerging Infectious Disease Laboratories. That is a level 4 national laboratory in the US that can work with live virus. So what they did is they took top predictions made by our models, and then they took those drugs that were predicted as most relevant and highly likely predictions, and then they validate them in the experimental lab. So they screened them for their efficacy against the virus in African monkey cells and then in human cells. The results of that experiment was that by screening those drugs that were predicted by the algorithm, we obtained a near 62% success rate, meaning that 62% of the drugs that were predicted by the model to work and that these experimentalists have tested in the lab turned out to really reduce viral infection. In contrast, if one would not use predictions at all, we would only get around 0.8% hit rate. So that's an order of magnitude improvement over alternative approaches, which is very, very exciting. And kind of going through this entire process from building the data set, running the state-of-the-art graph machine learning models, validate predictions produced by the models. There are a number of takeaway messages that I and my group have obtained from this project. And so I want to share some of them with you. So first is that this observation that zero-shot learning is indeed very important direction to pursue. I think this is a major gap that prevents routine use of state-of-the-art machine learning models for problems at the frontier of science. However, generalizing to new phenomena such as a new disease, emerging pathogen is still very hard and challenging. There are lots of algorithmic challenges there that need to be solved beyond GMeta algorithm. And second, what was very important is that while we somehow working very closely with domain experts here, we realized very quickly that it's not enough to simply produce these point-wise estimates or ranked list of predicted drugs, but we need to have a mechanism that will allow users, in our case, domain experts, virologists, biologists, to interact with machine learning models, provide feedbacks that can be integrated back into the model. And so that led us to developing various strategies that allow users to engage with GNN models in an effort to enable scientists to provide feedback on model development, to build trust in machine learning predictions, and ask what-if questions and receive predictions that can be interpreted meaningfully. And so in the context of this particular project, we first relied on GNN Explainer. That's one of the first explainability methods for graph neural networks that we published a year before that project took place. And so the key idea of GNN Explainer is to summarize where in the graph a GNN model looks for evidence for its prediction. And that is done by solving a small optimization task that aims to find a small subgraph most influential for the prediction made by the GNN model. And it does that through counterfactual reasoning in such a way that it finds the subgraph that when it is removed from the GNN model, the model would change the prediction by a large amount. And so that data that when removed from the model has a major impact on the model prediction would then constitute an explanatory subgraph the GNN Explainer provides. So one slide with a bit more detail. So the idea for GNN Explainer is that we start with a prediction f of x for a particular node or link x, and f is some GNN model like GMeta. And the output is an explanation, which is defined by GNN Explainer as a small subgraph m sub x. So it's a local explanation together with a small subset of node features. And M sub x can be thought of as adjacency mask that is optimized, and this is done by GNN Explainer in a post hoc manner, meaning that GNN Explainer is a post hoc tool that can be used with any GNN model. That's why it was easy for us to use it with GMeta. Intuition here is that a particular node V would be a good, should be part of an explanation if removing V from the graph will strongly decrease the probability of making prediction f of x. In that case, V is a good counterfactual explanation for the prediction. Now, we are not doing that at one node at a time, but we are really doing that by optimizing subgraph in a joint manner. So here is just an example of an explanation with GNN Explainer for one particular prediction. In this case, domain experts ask whether a form of statin will treat hyperlipidemia. So will this drug treat hyperlipidemia? And well, domain experts would want to know what is their disease treatment mechanism? How would that drug treat hyperlipidemia? Because providing such an information can give to domain experts insights about how they should go about designing experiments in the lab. So our GNN Explainer algorithm would then produce these small explanatory subgraphs that consist of some subset of nodes that are genes and different molecular pathways, biological functions that those genes are involved in that provide a good explanation for prediction made by the model. When we apply GNN Explainer in the context of the COVID-19 repurposing study that I mentioned, we made some very interesting observations. In particular, we wanted to know, well, is there something common to those drugs that were predicted correctly and were also validated experimentally and truly have inhibited and reduced viral infection? What we found is that by exploring and visualizing GNN explanations, we found that 76 out of 77 predicted drugs that successfully reduce viral infections do not really directly target the proteins that the virus attacks. Instead, those drugs rely on network-based actions. They kind of target proteins that are far away from the viral proteins, and those proteins in turn, due to some cascading effects, eventually mitigate the effect that virus has on human proteins. And so that was particularly a kind of interesting observation. It led to the discovery of this new group of drugs, which are now referred to as network drugs, because the way they exert their therapeutic effect is by relying on network and mechanisms. It also is a clear indication how graph machine learning in particular is the absolute necessity for these kind of studies, as it would not be possible to identify those drugs with representation learning algorithms that operate on other data modalities. Okay, in the last few minutes, I would just like to highlight a bit some of the very recent work that that is still ongoing in the lab, and that relates to the question of not only providing explanations or learning how to generate explanations, but well, it kind of goes one step further, which is once we have those explanations, how should we present them to users? And that's, I think it's a question that perhaps in other data modalities like images or language might not be so important. But in the context of graphs, it's incredibly important because it relates to this question of how should we lay out nodes or edges that constitute an explanation. So what we did recently was we examined a variety of different kinds of different strategies to present explanations to users based on whether we should be presenting neighboring nodes or entire subgraphs, or be presenting to users a series of disjoint linear pathways. And that relates to how human experts and humans actually can interpret and make sense of graphs, which is very different from how human experts are interpreting, say, image data, which we are much more used to. Which we are very often used to doing, but we are not so used to interpreting graphs when we talk about scientists from other domains. So we designed a tool called Drug Explorer that can that implements a variety of visual strategies for how to represent explanations through made by GNN explainer type algorithms. In particular, that can be done through these linear pathways or subgraphs, neighboring nodes. And we designed a user-centric study where we evaluated through interviews and studies with biomedical experts. So those were medical clinical researchers, those scientists who work in drug discovery, whether explanations can really help them improve decision-making in drug discovery. In particular, we were interested in knowing whether when we provide a prediction together with an explanation for that prediction made by graph neural network model, which we now know it's very crucial to have, is that more helpful to domain experts in deciding what are those drugs that were predicted that are most likely to be really effective in order to maximize the yield of downstream experiments in the lab and so on. And so we did that user-centric study, and the results of that showed that it certainly is very useful to present explanations in the form of these small protein and biological process graphs together with predictions to domain experts that help them substantially in making decisions about what are those predictions that they should trust and are likely to be biologically meaningful. And furthermore, we found that in general, visualizing subgraphs is most appealing to domain experts in the drug discovery space, more than just visualizing neighboring nodes or visualizing baselines. Okay, since I'm almost out of time, I will spend the remaining minute that I believe I have just with just a shout out on an initiative that we have that we started with several partnering universities earlier this year in an effort to provide AI-ready data sets and benchmarking resources and strategies for model evaluation that would cover the broad area of therapeutics development. And so this initiative is called Therapeutics Data Commons. It serves as a meeting point between domain scientists, who in this case would be biologists and medical researchers, who can identify what are meaningful tasks, what are meaningful data sets, and machine learning scientists who are developing new models, and in an effort to facilitate algorithmic and scientific advance in therapeutics. And the initiative has been growing very well. To date, we have over 26,000 downloads of TDC data sets, a variety of over 24,000 downloads of TDC software package, and 4,000 active users every month. TDC creates many opportunities for graphs. Those who work on graph machine learning might have noticed that there's quite a bit of interest that recently drug discovery has attained in graph machine learning community. Most current efforts have been focused just on one kind of graphs, and those are small molecules. There are many other types of graphs that have its own challenges, and I think can stimulate the development of new algorithms that are already present in TDC, as well as rich knowledge intensive, image intensive, language intensive graphs that can drive not only development of core new algorithms, but really also algorithms that are tackling some of the open challenges in drug discovery. Okay, with that, I will stop here. Papers, code, data are available at our lab website, zitniklab.hmsharvard.edu, and I would be also happy to take any questions if there is time for that. Thank you.
Marika, thank you so much for the amazing talk. Actually, we are out of time. So if anybody has any question, they can ask it in the chat section of Zoom, and possibly Marika can answer over there. By that, let's move on to our next speaker. It's a great pleasure for me to introduce our next speaker. Freddie Lecoux is the chief AI scientist at CourtAIX and a research associate at INRIA. Before joining CourtAIX, he was the AI R&D lead at the Accenture Technology Lab and a research scientist at IBM. He received his PhD from École des Mines de Saint-Étienne, if I pronounce it correctly. His research area is at the frontier of intelligent learning, reasoning system, and IoT, focusing on explainable AI. Pursuing his research, he won various awards, such as the Best Paper Awards from ISWC and ESWC, as well as Semantic Web Challenge Award from ISWC. Freddie, thank you for joining us here. The stage is all yours.
Thank you. Can you see the slides?
Yeah, we can see yours.
Okay, fantastic. So thank you for the invitation. So it's very my pleasure to be here with you today. So I'm going to spend the next 40 minutes presenting some of the work in the area of deep neural nets and explanation. So it's really on the mix of the two field on how you can explain deep neural network. And so I've spent the last couple of years, well, not only myself, but some of my team working on this topic. So I'm going to present some of a kind of perspective of where the field is going, what we think is good, what is not good, what might be, and where knowledge graph could be well useful, and at least where we try and where others try to plug knowledge graph for addressing challenges along the lines of deep neural nets. So as has been mentioned, I'm based in Montreal and in Canada. I'm leading a team of scientists and engineers which aim at pushing the limit of deep neural nets further, not in terms of precision and recall and accuracy or anything along the lines of precision, but much more in the lines of interpretability and explanation. So that's what my team have been trying to do, and the reason why is because my employer, so I'm part of the Thales group, and Thales is strongly in critical systems. So there are systems that that you put in trains, that you put in submarines, that you put on planes. So anything which is very critical. So anything where you push machine learning in those domains, well, you need to make sure that they do act and react and make decisions according to some kind of rules. And if there's something wrong, or if you want definitely to avoid that, you want kind of explanation back, either in real time, either post accidents, and always, not always for the developer, but also for the operators that is going to use it. So you have the links of the presentation. So the presentation, you can access it. It's up there. So in terms of scope, very quickly, so in the trustable AI system, there are many pillars. You have the responsibility part. So what do you define as something responsible for the company, or for the action that you're doing? So you define those, and that's part of one of the pillar of the trustable AI. There's the validity part. So anything when you put intelligent systems, they need to be valid. So you have some metric to evaluate how they're gonna detect object, or doing segmentation of images, doing planning, or whatever is the AI task, and you have way of validating those. So you need to make sure that that's valid under some particular constraints. You have some privacy preserving pillar, because we get data from the outside world, which might touching sensitive information. So how you make sure that when you build a system, you don't really abuse of whatever data. So, and it's very sensitive nowadays of the data leaks of major different companies and in many different kind of industries. And the other one is the what's explainable AI, and that's the other pillar which I'm touching it today. So, and it's really presenting the explanation and the reason why behind. So the way I structure, I'll start with introduction and motivations, and the way I usually present. So I'll go very quickly on the very first slide, because it's a workshop on the topic. So I guess you're familiar with the focus and the reason why you need the explanation. But if you start from from Facebook or Netflix that do provide recommendation of movies, or that do tag friends of the image, they have access to a lot of data, and their goal is to use all of the data that we do provide as customers, or our clients, or as users, and then they use all of this massive amount of data, and use all of this massive amount of data, they make recommendations, and they have all of this data they can use, and that's they really designed for machine learning systems. But at the end of the day, if they make the wrong recommendations, if they make a mistake in the tagging, if they make a mistake in making a wrong recommendation, it's not really the end of the world. It's not good. So, well, we may waste some time. We might get upset because some people have been tagged and they are the wrong person. But what we call, they are not critical system, in the sense that there's no really a life of a person in danger here. But if we think about critical systems, that system where you put machine learning models and systems in a submarine, for instance, where you detect particular things and elements. So here you have a team of people in the submarine, and they detect underwater mines from world wars, and they try to remove them. And it's a very critical and challenging task, because they may spend lots of time and energy in trying to removing something which is not a mine, and so they might lose money and time, or they might they might skip a mine which is actually a mine. So and they need tools and elements that say, okay, this is a mine because of, and whatever is the characteristics. They do define, they need a system that help them making the right decision. It's not only them making the right decision, the system should be here to provide, we detect something, and the reason why is whatever is the reasons. And the same if you push machine learning system in what we call autonomous trains. I know there's a lot of work on self-driving vehicles, and train is probably one of the closest in terms of reality, because it's running on rails, and the degree of freedom is quite limited. But still, it's still a challenging task. But still, if you do make a mistake, or if the system make mistakes, then who is accountable, and then you need system for the operators or the driver to make the right decision on time, and they need again some kind of explanation or reason. So if the system detects something on the way, if it's a plastic bag or if it's a person, I mean, that's different, right? And if you see very far away, you need to have some evidence of what is this particular object or obstacles obscuring the whale track. So there are critical systems, and you have even more. So you have plenty of examples where you have data which is biased, so the model is biased in some ways, and then when you try to detect particular type of persons or particular skin, then they make mistakes, and the explanation is, well, underlying because of the data that you have, and also because of the way model maybe have been trained, and that's very disrupting somehow, right? So and that's not good. That's not good for the field. That's not good for pushing machine learning in production, because there's a strong break. So, and you have all of those examples here of why we need explanations somehow. It's not like you have a system, you get some accuracy, and if you have bad accuracy, then you need to fix something, you need to rebalance the data, but you need to adjust your elements. So the explanation in a nutshell, that's we see it mainly while in the field as a black box. So maybe true, depending. Some people say, okay, well, a machine learning system should be a kind of a white box, and you should take the simplest model ever, so you can find easy explanations. So linear models are examples of model that you can easily interpret, because you have the features, you have a weight associated to, so that's easy. But sometimes, you know, while the data is not so easily, you cannot easily fit a very simple linear functions or to whatever you want to learn. So you have something much more complex, and that's where you have deep neural nets. But unfortunately, then if you have operators, that people who are not particularly expert in the field, they need to interact with the systems, and they start asking questions. And that's where it's usually you have the black box, they make decisions, you have existing techniques, but you use it a one-shot way. So, and people getting frustrated because they don't get the explanations, or sometimes they get something, but it's not really something that you can use for certification. So there's a strong field in software engineering, which is certification of your software. So anything which has been so far, it's not really aligned with what you need for certification. And then you have all the metrics and evaluations techniques. So where when you think about explanation, you think about something that you can comprehend, which is short and succinct, something that you can action, that you can reuse, which is accurate. And that's all the objective. That's what an explanation should bring. And then if you look any papers, any work, any of the latest work, any packages which is coming from Python. So you have many toolbox now, just to name a few. You have Captain from Facebook, you have the tools from Google, the pair and the toolkits. They are very fantastic toolkits. But then when you think about, okay, I need an explanations or tools that provide interpretations, which is short, actionable, reusable, accurate, and a human can comprehend, well, then those tools cannot fall short. They fall short, and it's not because those tools are not good. It's just that the way we focus is mainly on the from a machine learning, on the pure machine learning angle, right? So and then from a pure explanation perspective, you usually miss the end user evaluation, so validation in terms of what you really need. So yeah, so it's all fall short in terms of evaluation, and now I'll try to give a kind of a step back on explanation techniques, and just give you a range of, in terms of AI. So just forget about pure machine learning, but just step back. Explanation has been all over the place for the last 30, 40 years. Many people have been working on it back in the very early stage of expert systems and symbolic AI, where you have rules. It was already there. So, and it was always in the back of the head of people and designer, that they wanted to have some way of interpreting it. It just then somehow focus more on the accuracy rather than the explanation. And so if you look at the AI, and it's in here, what we simply did is just say, okay, in AI, where are the different domains? So you look at triple AI and each guy, They are the broader AI conferences. They mainly structure, and when you bid for papers and when you submit the paper, you pick one of those fields. It's planning, it's search, it's robotics, it's nudge and representation, NLP, machine learning, and all of those fields, they did address explanation in one way or the others. You will find papers and techniques. They do provide explanation. So I won't go through all of those different techniques. Won't have time in 40 minutes. We do have a tutorial at III 2022 in January that will cover most of the techniques, but today that's not the goal of my presentation. But most of the field, they did spend time. So just to give you an example, in planning, so in planning, you try to achieve a goal. You have an agent, a robot, and you have a set of actions. So you have a set of actions. You can go ahead, you can go left, you can go right, you can pick an object. So of the list of actions that you can take, and the goal is maybe to build a house or to build a house in a particular location, or whatever is the goal. And the action and the goal is to build those sequence of actions in a coherent way. Usually, you evaluate based on how you can build it end to end. You can have different, you have these junctions in the way of where you build your actions. So there are different ways. And the explanation is, well, how you did articulate the actions together. So usually if you take a particular object and you place on top of the other, well, the requirements is that you already get the scene and you get those subjects that you can pick them. You have the actions that you can pick and you can pick on top of it. So you all of those requirements and these actions, and then the goal is when you end up fitting the house, for instance, and so in all of those domains, from robotics to machine learning, multi-agent systems, they have mechanism for capturing explanation. So here I'm focusing much more on the deep learning dimensions. So deep learning is, well, obviously that's related to machine learning and computer vision and natural language processing with language models, but also in robotics, because they use visions, they use planning, and it's and behind the scene you do have deep neural nets for perceptions, and multi-agent systems. You do also have deep neural nets if you do reinforcement learning. So that's another way. So here I'm really focusing on deep neural nets. So now what I try to do is really try to convey the message that there have been some work done, and there's been a ton of work. I won't list all of the work which have been done in the different fields, and I try to structure in terms of what we think is good. So the good part of the work which has been done. I won't list all of them. I will miss many, so it's not an exhaustive presentation, but just give you a snapshot or an example of what's good, an example of what's bad, but still there's some interesting part of the bad. I define as a bad, so maybe not the good term, but something that you can still reuse. And the thing at the ugly as from an operator perspective, when I'm discussing with people, this is not what they're looking for. But still, there's some very interesting ideas. And so here, the talk is really aiming at being a bit provocative and saying, okay, there are those four dimensions: the good, the bad, the not so bad, and the ugly part of providing explanation. And they all have some interesting elements. And my conclusion to this talk is well, you can go multi-dimensional. Well, you can go one way or the other, but at the end, we conceal all of these different techniques, and the way to plug and to group them is using graphs, and that's the way. That's mainly my message here. Okay, so let's start with the good one. So the good is so here again is one example. There are many out there. It's not the majority of paper you find doing explanation, but it's what we call iterative and multimodal explainable AI system. So it's really a system. So whatever is your task, it's a perception or it's a planning. Well, here the illustration is on a perception task where you try to classify a particular object or classify an image, for instance. And here it's really just think about the process. So you have a system. The system is giving you, and that's a classifier. So it's classification of image. So you have many classes and give you the answers. Most of the system is good. I mean, we already reached that stage. And then the next stage will be okay, give me the reason why this is what you said it is. So you said it's a fish, so give me the reason why. And the system should get back to you and say, oh, you have much more green regions, which are kind of the fish part, and the red one, which push much more towards dog. And there's more green, so that's the reason why. And that's basically, you know, the super pixel one or the saliency map versions. So think about articulating this saliency map version in some kind of dialogue way for the users. And I think you can do it right now, and the people have been doing it. But think about it in a iterative way, and the user will keep interacting and say, okay, it sounds like, well, indeed, that sounds like a fish, and I'm kind of agree with that. But what kind of the examples are the most influential for these predictions? And again, while deep neural nets and machine learning, they're aiming and learning a function which fit the examples, and then you can easily find examples and say, okay, this is the closest example in my embedding in my latent space, and here is the closest one. And then you can give examples. Okay, this is, okay, so from the image, this is the important features, which I think it is important, and this is the example which are the closest one. And you can keep going. You can keep going and say, okay, but now what if I do change the background? Maybe you learn some from the background, because when I look at the region in green, there's a lot of things in green. It sounds like it's the background, and I don't think it's really a fish part. So, and then you remove the background and say, well, it's still a fish even if you remove the background. And then imagine you can keep going and say, okay, what if I remove some of the other part, and you keep interacting and you keep challenging the system if you want, and you keep challenging to get much more insight of what you get. So it's not like, so really the good part of those systems is that there are systems that you can question, you can interact with, and they help you building your confidence in the systems. And those systems, they do handle human follow-up questions. You keep going, you keep iterating up to you convince, right? So when you're human and you say, okay, explain me why you did that exactly, and then it's not usually, they don't give you back only one thing and you're done. You still make question. Okay, well, I don't think so. You're challenging a bit, right? So, and this is kind of what an explanation related system should be doing. And human machine interaction, they are foundational, and they should be foundational for building XAI systems. Example and prototypes, they do help. And also why we need such kind of interaction is because myself, as a non-expert in the field, I may ask different questions than a pure expert. That's definitely, when it's looking for a minds, is looking for particular shadow and say, okay, well, but those shadow, I know this is kind of the shallow part of the water, which make these reflections, and then you can go much deeper. And as a Lambda user, I won't ask those questions, but I still want an explanation which I do understand. So the pretty good interactions. You have the human in the loop from the start, from the to the end. And the construction, you do interactive explanation search. And validation, you have the operator as opposed to the developer, and you can even consider the developer, so it's really for any operators. And the knowledge part is you do consider the domain knowledge, which is required at the beginning. So you do provide different interactions depending on who you interact with. Okay, now if I move to the next one, which is the not so bad. So this is a picture of some work which has been done by MIT and Stanford, has been presenting, I think, at Neurosymbolic 2020. And there's very interesting work where they try to understand the inside of the neural networks, and they try to label neurons. So you pick a target layers and you want to have a label of it. Initial work from MIT, this is the work on the left-hand side. They can associate a label to a unit, and they basically say, if I have an image, I pass it through the network, and I pick a layer and say, this is the unit, this unit is responsible of, and you have an IOU score, which is an intersection of a UNIO score, that give you kind of the interpretability of this neuron to be activated on a particular concept. And some folks from Stanford and MIT presented at Rdfs some work where now they not only label one neuron per one concept, but they use conjunction, disjunctions, and negations. So for instance, if you pick one on the left-hand side, where you detect a swimming hole at the end, they have the units. So I don't remember which layer is it in the neural net architectures, but you have the different neural net architectures, and they say the neuron 483 it's water or river, and that's not blue. And you say, okay, but that's interesting, but what you're doing with it? So what you're doing with this, it's okay, basically, if you can understand the label and the semantic of neurons, you can start composing and you can start using and manipulating neurons. And what they try, they say, okay, let's use an image, and they say, okay, you need to not be blue. So they color the thing in blue. So you know the water, it's greenish. They change it to blue, and they pass it to the network, and now they don't capture this to be a swimming hole, but to be either a grotto or not spring, depending on which architecture you use. So that means that they give you information of what the neural network is really capturing, and that in a much more human interpretable way. So that's go really further. So that's why I'm calling this. It's not so bad, and it's very interesting work here to be trying out. So that's something. So unfortunately, there's no human interaction. It's really a one shot. It's based on co-self-firing. The interpretability is based on intersectional union, and the knowledge is kind of is implicit. So you use the label of the image that you get. So they start from the segmentation task, or they have all the labels, and that's what you need. That's what you use for labeling your neurons. Okay, so now the bad part. So the bad part is really the feature visualization work. So that's some work from OpenAI. I mean, it's very impressive. They build what's the name of the library is called Lucid. It's very brilliant work. So I think they try 13 architectures, and basically they visualize any features at the neuron level. And you can see, from a human perspective, you can see the link here, and you can see for a neuron. So here, for instance, for unit 118 in WestNet 50, the clip version of it, in the layer 4, this capturing kind of pumpkin related, and then you see all the different examples and the one. So this one I mentioned it in the bad version because it's you still have the labels and the examples, but it's not as well structured as the one before. So here when I think about the good, the bad, the not so good, and the ugly part is really at the interpretation level. What kind of interpretation I can make out of it? So it's difficult to make interpretation. So there's no human interactions. It's based on neuron activation. It's mainly aiming at the developer at the end, and the knowledge is quite often implicit. It's based on the vocabulary that you have, but it's working much better when you do have language / image models like CLIP, which is one of the foundational language model which do where you generate image from text, for instance. And you need both. But if you take a pure ResNet that's built on image classification, it's not as good. Or if you can try it yourself. But you see on the right hand side a pure ResNet 50 built for image classification. You see the abstract representation of units. They are not as great as the one that you see on the left hand side. And that's because of the alignment between language and image. And that's why, depending on which architecture you use, you might lose this interpretability level, and you may say, okay, well, what does it really capture towards the end? Okay, so if I move now to the ugly part, which is, well, to be honest, where a lot of the work which has been done in the machine learning community is what's called saliency maps or superpixels. And why do I say that's the ugly part? Is because every year you probably have 5-6 new way of computing saliency maps. And the way it's evaluated, it's mainly qualitative. It's mainly qualitative, so it's mainly looks good, so it sounds like it does recognize and does fit the pixel, the input pixel, which are responsible for this particular classification. But quantitative wise, there are a few metrics, but it's still subject to debate. There is no really pure, and the reason why that's kind of it's tricky to evaluate. There's no really ground truth of what's an explanation. So I think if we'll have to get started from a image the data set with the explanation where humans are agree on the explanation, I mean, that would have been a different story, because we will have tried to fit the best the ground truth, but there's no such thing. So it's like every approach comes with different things, focusing on different parts. It looks good, but it's difficult to do and to make any interpretation. So sometimes when you show to the user, oh, you need to detect this object. Oh, I have the explanation, and you show the saliency maps or the superpixel, and then you can use many techniques from pure gradient based or perturbation based, and you have many of those techniques, and whatever you come up with, you see those superpixel and say, okay, it sounds about right, but sometimes you can cherry pick and find pretty good examples where you say, okay, that's the one you should be focusing on to get the car, because getting on the wheel and getting on the length of the vehicle. But sometimes it's completely off, and still the prediction is still good. So then you can question, well, is it really an explanation? There sounds like there's something going on in the network when they do backpropagations and when they do perturbations. That's something it's kind of off. So that's the kind of the ugly part. There's no human interaction. It's purely in the architecture. It's purely mainly qualitative. It's highly subjective. And there's no really knowledge required. It's pure working on the architectures, and you don't need outside information for doing any interpretation. Okay, so that's the way I structure it. So now I'm going quickly to 2 examples. So I have 12 more minutes to go, very quickly to give you an idea of the work we have been doing and give you an idea of, and it's pretty easy and pretty simple, how we will combine and use graph for solving the issues of 2-hard explanation. So if you use state-of-the-art machine learning applied to critical system, while you try to detect that obstacles on the rail track, while off the shelf, you get lumber mill with a 59%. And actually you're missing boulders and railway, because while you do object detection, there's a threshold. And if you didn't fine tuning, well, obviously you don't get good result at the first place, but here's what you get. And what you want is, you really want to get this boulder to be much higher up and lumber mill to be lower down, because you care about the obstacle on the rail track. So if you apply explanation, well, saliency map techniques, this is what you get: version 1, version 2, another version. And but that's not of use as a human. So that's why I start while ending with this ugly part on saliency map. Okay, you get a neural net, it does classification, and the explanation is the saliency map. Okay, you end up with that, but the neural network is not doing a good job. So yeah, tricky, right? So let's say so why we get this explanation. So if you look at lumber mill, so lumber mill is kind of it's a sawmill or lumber mill. It's a facility where you have logs and they cut and timber, and you see lumber, and the focus here it's the log that you see on the left hand side, and you have the description. So what's missing here? It's while you're missing that they should be well, if that's really a lumber mill, you should have probably more logs, and you should have also a warehouse and probably kind of tool sets for cutting lumps. So a much more structured information and much more contextualized information. And what we think is, if you really want to detect these obstacles or this boulder here, you should give it more context. So what we try to do is we go through DBpedia, we capture the different concepts which captured, even with a low score, and we try to see co-occurrence of object detected, and try to see, well, if your big boulders cause accidents and they form tracks and they form vehicles, when they, well, that means when they put in a context, that means that might be an obstacle. So, and then you try to figure out what might be the relevant co-occurrence of text that make the explanation of the scene right. And what we're aiming at doing is, we want to move from the left-hand side to the right-hand side. And what you see, the difference is mainly that now we do identify tunnel, boulder with a score still the same as the one on the left-hand side, but it's boosted up, so from 9% to 81%. And the goal is really not to retrain what the model is what it is, right? And we basically want to play with the output of what we get. And the output is really try to figure out what's the context around if in borders there is deformed tract in co-occurrence with other documents, in the other documents, that means they probably, they should be boosted up slightly in terms of scores. And that's what that's what we're aiming at doing, try to find which objects are detected, which one makes sense in the context. And if lumber mill, there's no other object associated, so there's no more lungs, there's no sawmill, there's no manufacturing, there's no house, there's no such things. Well, it's kind of alone, so maybe you should reduce it down. And that's what we try. It's we end up with this platform, which basically illustrate the co-occurrence as the graph and connect the different entities together, and end up providing the explanation of why we think it's a boulder and that how it's connected to the other elements and concepts, and again using a very targeted domain where the co-occurrence of terms, or you can say the co-occurrence, but then you can start using language model in a particular domain, or if you have documentations in your field, that's something you can use and use this particular similarity of embeddings. You can use many other ways. Okay, I'll pass it to that. So there are a few reference of papers that we publish at KR and ISWIC, for instance. Another one I want to go, so a few minutes ago, So on some visual questions, so completely different problem. Now you have an image and you want to ask a textual questions on an image. Could be an image, a video, whatever multimedia, but something with pixels. And so it's not a new problem that's been posed a few years back. Most of the technique, they use combination of CNNs and RNNs for solving the problem. They've been starting in 2014 with some data sets, and we have very nice and interesting results. But there are limitations. So, and the reason why is if you ask a question where the answer is not in the image, well, there's no way they can figure out how to find the answer, and the knowledge is limited. So the only knowledge that you have is well, all the training data that you get as training, and the object that you detect in the image, and the token that you have in the question. That's it. So there's a new kind of domain which is now called open knowledge, or visual question solving with open knowledge, which basically use now knowledge graph related techniques or structured information that you can find. And the state of the art, it's Mavex, CRISP, and ConceptBERT. The state of the art where they do retrieval to retrieve different entities on the web, similar images, and that's one technique to try to boost the architectures with much more knowledge. And graph embeddings, we use ConceptNet as a graph, and you try to compute the embeddings, and then you plug somehow the similarity of entities together, so then they can help. So that you have work. So our goal was not really to make them better, well, still the objective, but much more to find explanation of visual question solving system with open knowledge. So that was the main goal. And here what you see on the right hand side is what we ended up. So so here you have a semis. And we use a combination of different techniques. So we use state-of-the-art architectures. We plug transport optimal techniques for mapping features from visual embedding space to the much more language embedding space, and try to see how those how tokens in a question and how objects in an image might be linked together at the embedding space. And also what you see after the question, you see terms. So if I look at the kind of the matrix map, you see the question, what breed of cat is this? And then you see terms after that. And those terms, we add facts from ConceptNet as the knowledge graph. So simis, breed, cat, simis, aggressive, cat, simis. So we add a few ones. And the goal was to say, well, so we think to answer that question, there's not enough information on the picture. So we need to find some kind of more information here. And we use ConceptNet, we use the facts. And the core question was to retrieve those facts and make, first interpretable and make better results. So let me check on time. So a few 4 minutes. So I won't describe the architectures, but it's mainly a classic visual question answering module plugged with a fact retrieval module, and the fact retrieval module is going after the fact that you can get in your knowledge graph and try to capture the most relevant concept that you need to add in addition to your questions. And those facts, they do connect tokens of your questions, and they connect the objects, which are concept or classes in the images. And you try to add fact that's related to, and the objectives are to see, well, do facts, do they really boost the scores, and do they provide explanations? So that means if you can connect tokens and objects, not in a strict way. So if you say, oh, there's the cat detected and there's a breed in the question, maybe it's not like the Samis is a breed, well, as a breed cat, Samis breed and cat are connected. You may have Samis breed and animals, and then further on you may have cats. So it's kind of a much more complex sequence of facts. And surprisingly, I think the most important result we get is this 54.7. So that means we didn't crack yet how you can find the best facts, but if you put all kind of relevant facts, you can reach 54.7% in terms of accuracy, and the state of the art now is at 40.5%. So that's a huge jump. So if we use our approach, which we call XVQA, we reached 39.7, which is not close to the state of the art. And the main reason why is because we use a subset of those facts. So we try to reduce it even shorter for computation perspective. But by reducing it further, you don't reach the state of the art. But if you add all the facts which are relevant, you reach 54.7, which is a huge. So that means there's a huge gap between the 40 that state of the art get and the 54 that you can get by adding relevant fact from a graph. So that was very kind of mind-blowing for us. I mean, in terms of where you can go and where is the state of the art now. We can move from 40 to 54. That's huge. I mean, it's a very complex task here because the state of the art is at 40-ish%, and that's very complex because the answers is usually not in the image. So that's tricky, right? And then you have a few other examples where you see what oceans are those surfers in. The answers is Pacific. And here you need to connect, surfing is an activity in Pacific and surfboard is related to oceans. And that's kind of the main fact which has been used here for connecting the entities in the question, like oceans and surfers, and the object detecting on the image, like surfboards and surfers. So the things on the left-hand side, again, are questions plus graph concept. And the thing on the bottom, they are concepts captured if you do object detections in an image. And we have a few more examples. So yeah, I'm kind of quite short. Yeah, 1 minute to go. Again, you have the presentations links further on. But yeah, in terms of what we learn is retrieval explanation. Well, it's complex, but it does bring added value. Definitely bring added value. The question now is, well, how you do subselect those facts. And that's an open question, but there is a huge potential for explanations and even also for boosting results. Okay, so I'll squeeze that and move to conclusions today. So yeah, so I presented the good, the bad, not so bad, and the good part of doing explanation in machine learning. And I also give you 2 examples of where we use graph, knowledge graph, mainly concept net here or domain knowledge. And I think it's if we want to move the gap between explanation for a developer and explanation for anyone at any time in any context for any task, graph has a huge role here. So yeah, so that's concluding my talk. I'm open if you have time, if we have time for a question now.
Thank you, Freddie, for the amazing talk. Do we have any question here? I can't myself ask you some kind of open-ended question. So I'm interested to know what are your thoughts on the evaluation challenges for interpretability system, especially for knowledge graphs. So basically, most of the time we end up relying on human evaluation for evaluating these techniques. So I'm wondering how we can conduct human evaluation on knowledge graphs, or are they even reasonable or enough for evaluating these interpretability systems on knowledge graphs? So what are your thoughts on that?
I think we need the user in the loop anyway. I mean, explanation is redesigned for users, so and you want to take an action of it. So so out of the explanation, so I think the human should be here for curating and for evaluating that the system is getting the right thing. So that's for sure. And in terms of the use of knowledge graph, you can. So the way we're considering graph in our context is for while machine learning and deep learning, they're very good in figure out features and find important elements in the data that will figure out patterns, right? But they're missing the whole information which is not in there, but which is out there, which as a human we use for making rational of decision. And I think there's some important information, and the question is really which information is it that could be used for kind of contextualizing the task and contextualizing the explanation, which is very important. So I think graph is important for contextualizing and kind of securing a domain when you can ask you can ask questions and you can validate the results. But I don't think we can skip the user part. So when I'm interacting with users, the required explanation, I need to understand what they need to understand. And whatever I build, they need to digest whatever is the explanation. So, and sometimes they are not able to do it. So we need to adapt add a few layers of abstractions for them to understand. But I don't think the user is really the crucial part here.
Thank you so much for your answer. I think we are short on time. So again, thank you for your great talk. And let's move on to our last contributor talk. Rajiv Sambasivan is a machine learning SME at ArangoDB. He received his PhD from Chennai Institute. His research focused in the development of practical machine learning methods for big data sets. Rajiv, the stage is all yours.
Thank you. Can you see me?
Yes.
Hear me? All right. Great. Let me share my screen. All right. Okay. So, my talk today is going to be about about some of the explainable graph machine learning models we are building with ArangoDB. ArangoDB is a graph database, and we are headquartered both in the Bay Area as well as in Cologne. The work that I'm presenting here is the work that's developed by the machine learning team at ArangoDB. It's just a sample of the work. So with that said, here's the team. So the work that we are presenting today falls under the category of providing explanations for different tasks based on graph models. So the work is developed with tools in the ArangoML ecosystem. It's all open source. We're presenting 3 examples today. Each of them is a separate application, and the presentation will follow the following pattern. So first we describe the problem, then we provide a sketch of the solution, and then we provide some salient results. So the first example we have is the application of graphs in managing help desk tickets. So the problems as follows. So it turns out that the data actually is from the data set actually is from a help desk application that is used for resolving IT problems. IT problems for resolving IT problems. So it turns out the ticket resolution process actually is a 3-step process. The first step is understanding the ticket. So when a ticket is submitted, the analyst reads the ticket, understands the issue, and then after that assigns a developer or an analyst to fix the issue based on his understanding of the ticket. And then finally the developer or the analyst actually fixes the issue. So the key aspect here, which is the focus of this work, is on the ticket assignment step. So it turns out that this ticket assignment is like can be very problematic. It turns out that errors in ticket assignment are actually fairly common, and basically errors in assignment translate to both increases in cost as well as time to resolution. So if you by identifying tickets that are going to be complex to resolve, you can integrate error proofing methods that will that will make sure that the triaging of the ticket is done carefully and correctly. So for this particular data set, it turns out that most tickets, about 50% of the tickets, can be resolved in with just one analyst assignment. And then there's like a long tail of tickets that have like 2 or more analysts to resolve it. So for the purpose of this application, a ticket is deemed complex if it requires more than 2 analysts to resolve it. So it turns out that the information that is associated with the ticket, with the resolution of a ticket, can be variable. Some tickets are not, for example, like some tickets don't require like interaction with a vendor, while some do. So we can abstract the ticket resolution process as a graph with these 3 abstractions. So there's the customer who submits the incident. There's the description of the incident. There is the support organization that that analyzes the ticket and works on it. And then there is the vendor that actually that you may need to interact on some tickets. So the task is actually the complexity of resolution is a property or an attribute of the incident node, and the approach that we've used is based on a paper by Schlittkel for applying graph convolutional networks on relational data. So we actually determined the hyperparameters for this for the neural network that we needed for this application through hyperparameter optimization experiments. So the results we found that the GCN approach that Schlittkel had developed was fairly good. We got about 85% accuracy in predicting ticket resolution complexity. Interestingly, actually, the node embeddings that we got from the neural network provide some really interesting insights. So it turns out that there is this clustering of both incidents as well as customers using the help desk. You have here's a t-SNE plot of the embeddings obtained from the neural network. So you can see the left one is it shows that you can see that customers cluster together, and the right one shows tickets cluster together. So that's the first application that we wanted to share. So the second application is deals with application of graphs to characterizing online user activity. So people want to characterize online user activity for reasons such as improving the user experience for an application that you've developed, or to understand your user community. So social networks, social network theory provides many tools to understand online user activity. So user activity, it turns out that in most cases you can model user activity as a graph, and graph theoretical ideas are also very useful. We actually applied this, took an example from a real world online retail store that sells novelty gift items. And we actually focused on the activities of a particular subgroup of users, those who are frequent visitors to the store. So for this study, we deemed a shopper to be a frequent shopper if he had made 5 or more visits to the store. So we can actually model the purchase activity of the online shoppers as a bipartite graphs, with the users and the store inventory representing the vertex sets. So it turns out that if you just if you just model the purchase activity as I just described, with users having edges to the items that they purchased, such a graph is like not very amenable to analysis, because of typical user makes very small number of purchases because it's a retail store. So we had to refine this graph by using an idea that is in retail analytics called the RFM score. So the RFM is an acronym for recency, frequency, and the monetary value. So the idea is that the value of a customer can be captured by how recently he has visited the store, the number of visits he has made to the store, and the amount of money that he has spent at the store. So we actually weight these 3 attributes together and then determine a score, an RFM score for the customer. So the weights for each of the parameters is something that you need to specify. Then we actually regress the RFM score versus the customer's purchases, and using the lasso, and it turns out that you can actually explain a large portion of, like, I think it's like 86% of the customer value of the frequent shopper group with like 75 inventory items out of a total of 2,600 inventory items. So there's GM has actually developed a general framework for analysis of bipartite graphs across a variety of applications. Using ideas such as projection graphs and clustering coefficients that are defined specifically for bipartite graphs. So we applied those an implementation of this is available in the NetworkX package. So we used the ideas discussed in this paper and the NetworkX package to actually to mine the insights about this group. The other idea that we applied was matrix factorization, actually non-negative matrix factorization, because like the incidence matrix of the bipartite graph, the purchase graph, is strictly non-negative. So a user can either makes a purchase of an item, in which case it's a positive number, it's a positive quantity, or doesn't make a purchase, in which case it is 0. So when we apply matrix factorization to the incidence matrix, we get you can actually view this as a dictionary learning exercise, and you get like a sparse dictionary that can explain most of the purchases of the frequent shopper group and an activation matrix. So the sparse dictionary basically gives you a grouping of partitions the inventory into different groups, and that tells you that kind of gives you one grouping of customer taste. So some of the results we found was that the frequent shopper community has cliques, and then here is the as we found clusters of different sizes. we found that each cluster has basically a specific affinity, has affinities towards a particular dictionary item. So, for example, cluster 0 has affinity towards the first dictionary item. So that is the retail example. So the third example is actually using using graphs to model functional data. So this so essentially in supervised learning we want to learn a decision function or a regression function, and in functional data each sample is a function. So this is the key idea, that each sample is actually a function. Rather than dealing with data, we deal with functions. So a function can be viewed as a bipartite graph with the domain and the image representing the disjoint sets, vertex sets. So it turns out that functional data is, people have used functional data to model problems in many domains, and Ulla's paper is a very interesting survey paper. So we actually looked at an application for time series data. So it turns out that many time series applications can be viewed as functional data. So the particular application that we will discuss today pertains to the yield curve of the U.S. Treasury bonds. So U.S. Treasury bonds basically are come as they come at they are debt instruments issued by the U.S. government. They come in a range of maturities, starting with short term, which is like 1 month, to long term, which is like 30 years. So, and to make this concrete, for example, here is this data is available. Here is here's a picture from the Treasury website. As you can see that every day this is available. So you have data, you have the yield that is 0.08 associated with the bond with 1 month of maturity, and you have the 30-year bond associated with a yield of 2.04. As you can see here, the short-term yields have lower values than the long-term yields. So the key idea is, given historic data about the yield curve, can we predict the yield curve in the future? So the yield curve is the set of these 12 or 13 maturities and their associated yields. So together, each of these ordered pairs constitute the functional data. So to do this, the approach we used is similar to the Kalman filter. So the idea is, so the Kalman filter idea is commonly used to track a moving object. So given you get a noisy measurement from a moving object, given so you have a model to predict the location of the object. You get you make a prediction for the location of the object. Then the measurement from the object's location is received, and then you reconcile your prediction with the actual location. So and then you repeat the process so the idea is you apply this idea to actually track the motion of the object. So we do the same thing here to track the motion of the evolution of the yield curve. So we use a Gaussian process. We develop a Gaussian process. We fit a function using a Gaussian process using data for days 1 through n, and then make a prediction, which is the posterior mean of the Gaussian process for the day n+1. And then you observe the yield curve for day n+1, and then we reconcile the GP model with the observation. So the details of this process are available in this paper, and so there are two. We compared the this functional data approach with two commonly used methods to forecast the yield curve. One is a time series method, vector auto, the VAR method, and then the other is a classic Nelson-Segan model. So it turns out that so here are the results. So it turns out that the functional data method actually does better than the other two methods for regions of the yield curve 2 years and later. So the medium term region and the long term region, it does better than the competing methods. So there is a significance to this. It turns out that the long term, I mean, in a good economy, they actually the long term, the shape of the yield curve, where the long term prediction is actually the long term yields are better than the short term yields, is actually is a phenomenon that happens only when the economy is doing well. So financial analysts and economists actually look at the yield curve to kind of like get a sense of how the. So here's an example of the yield curve from 2007. You can see that this is when we had the financial crisis, the housing bubble. So that was you can see that the long-term yield is lower than the short-term yield, and this is the yield curve in a healthy economy. So,
excuse me, Rajiv.
Yes.
Actually, you're over time. Can you please try to?
Yeah, sure.
Yeah, close up your. Thank you.
So to conclude, we have like we presented 3 examples of performing machine learning on graphs. So one was applying a neural model on relational data for node classification in the ticket assignment example. The other was using matrix factorization and social network theory to characterize online shopping behavior. And the third one was to use functional data to predict the US treasury yield curve. So these are a sample of problems that we are working on. We are very interested in hearing about these or variations of these techniques to solve problems in other areas. We would love to hear about feedback about this. We have a Slack channel. Here is the URL. We meet on Tuesdays. This is open to everybody, and we'd be delighted to collaborate on ideas. So yeah, that sums up what I had to say.
Rajiv, thank you so much for your great talk, and apparently we are over time. So if there was any question, hopefully they can contact you after the workshop and answer question directly from you. By that, we are done with our last talk. I'm going to invite Samir to join me again here on the stage and have our closing remarks. Samir? Oh,
right. Can everybody see my?
Yeah, you good.
You can hear me and see me, right? Okay, so with this, we're at the end of the workshop and of the conference as well. So I want to thank all the organizers, Pouya, Pasquale, Mathias, for putting together a pretty exciting program. I especially want to thank Pouya. I mean, he's been the face of it today if you attended the workshop, but also behind the scenes, he's been key in pretty much doing the whole workshop by himself. So yeah, thanks a lot to him. I again want to thank all of our speakers. We had a really, really nice set of talks, which were coming at it from very different perspectives, but also common and the kind of diversity we expected by when we were thinking of holding this workshop. I think we attained with these amazing speakers. So yeah, I think in the end, we should just few thoughts about the future of XGML, next year and beyond. In particularly, if you have any feedback or ideas about what we should be doing with this workshop, let us know. For example, should it be at AKBC next year? Are there other venues which, like maybe a machine learning one or I don't know whether graph-based stuff like KDD or something would be a better option. Are there communities that we should be reaching out to? So we had speakers from semantic web and machine learning and all kinds of applications as well. But are there communities that we just haven't thought about? Ideas for other speakers that are doing amazing work that we just missed, but you know about, let us know. Any thoughts about the format of the workshop? Should it be more interactive? Should it be not? Presumably the next version will be in person, but maybe not. And then how to have it. For any of these ideas and feedback, please email Pouya, and we'll be really happy to, even if you're actually interested in being part of the organization, it'll be great. So with that, I'll thank everyone for attending or listening to this recording, and we will see you later. Thank you.